as the president of Academy of Discrete Mathematics and Applications, and also is on the board of management of Atmiya University, which is a state private university located at Rajkot. So now I hand over the session to you, sir.
Thank you, Aditi, for your kind words. Very warm welcome to all the participants and senior graph theorists present over this virtual platform. I am very happy and feel honored to introduce today's keynote speaker, Professor Ambet Vijay Kumar, who is hailing from God's own country, Kerala. He is presently Professor Emeritus at Cochin University for Science and Technology, Cochin. He did his MSc and PhD from the same university. He also worked at Regional Engineering College, Calicut, who is presently recognized as a National Institute of Technology as NIT Calicut. His research interest is discrete mathematics, graph theory, graph spectra, and graph energy, as well as distance energy, and so on. He has supervised 12 PhD students, and popularity of his 70 publications can be identified by H index 13. He has delivered invited talk at various national and international conferences at India and abroad, countries like Hungary, Canada, Italy, Taiwan, Czech Republic, and so on. He is also a member of Ramanujan Mathematical Society, Indian Mathematical Society, American Mathematical Society, and so on. He is also presently working as the Vice President of Ramanujan Mathematical Society for the term of 2019 to 2022. And adding to this profile, and I feel very honored to mention that he has interviewed Honorable Dr. APJ Abdul Kalam, former President of our country, as well as Professor C.R. Rao, Robert Denway, President of Mathematical Association of America, and Michael Bansey of ANU. And he is also working hard for the popularization of mathematics in our country and globally, as he is working as a regional coordinator of Indian National Mathematical Olympiad for the year 1990 and to 2017. He has also contributed more than 60 popular articles on various aspects of mathematics in Malayalam, his mother tongue, and English. I am very happy to mention about the title of his talk. Is very catchy, sir, that his keynote address is entitled as Graph Theory from Bridges and Chessboards to World Wide Web and Beyond. Let us listen Dr. Ambed Vijay Kumar. Sir.
Thank you very much, Professor Vaidya. And Dr. Chirag Barsara, let me first of all congratulate all of you for organizing this conference and giving me a chance to present some recent developments in graph theory. So to save time, I will switch over to my share sliding, and I'll be happy if the organizers tell me 2-3 minutes before when I should stop, because I will not be able to look at the timings. Is it okay?
Yes, sir. Yes, sir.
Okay. So what I'm going to talk as a keynote is roughly what is happening in graph theory these days, and also what was happening about since 1736. The speakers in the inaugural session mentioned about epidemiology and COVID issues, and the interdisciplinary nature of discrete mathematics. And I am precisely what I am going to do, especially for the young researchers and students, is to showcase major Indian contributions to these subjects. I will always start my presentation paying homage to a very inspiring nation builder and teacher, Dr. APJ Abdul Kalam. The quote that I have taken today is, "Climbing to the top demands strength, whether it is to the top of my Mount Everest or to the top of your career." So I wish all the best for all the participants in this program. As you all know, graph theory began as a solution to a very simple looking problem called the Königsberg Bridge problem, which is actually a solution of a problem relating to the geometry of position. Geometria situs is the Latin word for graph theory, which is essentially due to Leonhard Euler. But let me tell my friends that the term graph was not used by Euler in his presentation, but instead it was done by James Joseph Sylvester, the bearded man that I have shown in the left side, a British mathematician, in his paper on chemistry and algebra, which appeared in the very, very prestigious journal Nature. And all of you know the problem, so I'm not going to spend on it. So 1736 is the beginning of graph theory, but 1936 is the year when we had the first book on graph theory, Theory of Finite and Infinite Graphs, Theorie der Endlichen und Unendlichen Graphen, by Jens Koenig, this book is by Jens Koenig. And the graph theory 1736-1936 is a wonderful book by Biggs, Lloyd, and Wilson. Those who want to look at the history of graph theory, developments in graph theory till 1936. As you all know, graph theory is a study of symmetric binary relation. So just handshakes. You see here different types of handshakes. And as you know, there is a statutory warning that you are not supposed to shake hands to avoid the spread of coronavirus. So let us, for the sake of mathematics, let us shake hands. And when two people meet, they shake hands or they don't shake hands. This is shake hand by 6 people, first person shaking hands with the other, second one, and the last person also shaking hands with the first one. So what we call in graph theory is what is called a cycle. This is also a handshake, but the last person is not shaking hands with the first one. So why we call in graph theory, this is a path. And this is where all people shake hands with one person, maybe the CEO of a company or a head of the institution like vice chancellor, expressing solidarity. So this is what we call is a star in the language of graph theory. So basic principle between in graph theory is what's called the Euler's handshaking lemma, which says something about handshakes. So let me start this with a small puzzle. My friend Chirag invites 6 guests for his birthday party. Sorry for this hair. My good old friend Samir, myself, Sushil, Pooja, Komal, and Yogesh. When they arrive, they shake hands with each other. Samir asks, how many handshakes does this mean? Sushil says 7 into 6, 42. Pooja feels this is too much. Komal wanted more time to think as if it is a great problem, and Vijay takes a anticipatory bill. He says, I don't know. And Yogesh settles with an answer 21. And I am asking you, what is your answer? You can think and give your answers later. So this is a very simple looking puzzle, which also uses the fundamental theorem of graph theory. To start with, let me take you to the coloring problem, which is very notorious and very famous because of several things. So if you look at the map of India, I want to color the different states of the country using different colors with the condition that no 2 adjacent states have the same color. So consequently, can I do with the 2, 3, or 4? That was the puzzle that was disturbing all mathematicians till 1974, based on a question asked by a student in his class, Francis Guthrie. Francis Guthrie and Frederick Guthrie were students of De Morgan, Augustus De Morgan. You know De Morgan laws in set theory and many mathematical results. But De Morgan was a very good teacher. He didn't know the answer. Therefore, he asked the great Sir William Rowan Hamilton, this is Hamilton, whether he knows the answer of that problem, whether 4 colors are sufficient to color any map, provided adjacent countries do not receive the same color. So here in the map of India, you know, Kerala, Karnataka, and Tamil Nadu have common borders mutually. Gujarat is colored with the green. So because Kerala is adjacent to Tamil Nadu and Tamil Nadu is adjacent to Karnataka and Karnataka is adjacent to Kerala, adjacency means they share a common boundary line. I'm sure all of you agree that you require at least 3 colors because Tamil Nadu is yellow, Kerala is red, and Karnataka is green. So you will require at least 3 colors. So the basic question that you can ask is, can you extend the 3 coloring of the states of India starting from Tamil Nadu, Kerala, and Karnataka to the whole of India? This was a coloring problem whose date of birth is 23rd October 1852. And on June 21, 1976, Kenneth Appel and Wolfgang Haken of University of Illinois, along with computer programmer John Koch, solved the 4-color problem using 1,200 hours of computer calculations and became the first such theorem in the history of mathematics where computers were used to prove mathematical theorems. So this came as a newspaper event in 1976. They said that, but the 4-color conjectures were being proved by 2 University of Illinois mathematicians. They had an invaluable tool that earlier mathematicians lacked, namely the modern computers. The proof of the 4-color conjecture is unlikely to be of applied significance. Nevertheless, what has been accomplished is a major intellectual feat. So whether it was proved using computers or not, the solution of the 4-color conjecture after plenty of years was a remarkable success among mathematicians. So when 2 people shake hands, it's just a finite thing or a small thing, but several people shake hands and several people are related, you get a network. And we are familiar with the word network because of several reasons, and most recently the COVID pandemic, epidemiological network. So we have the Indian Railway Network and the Air India Network, and the networks is very, very important these days. I will take one more problem puzzle in the chessboards to find the minimum number of queens that can be placed on an n by n chessboard such that each square is occupied or attacked by a queen. And for the standard 8 by 8 chessboard, it is 5. But it's very surprising and interesting to note that there are 4,860 different possibilities, different types of solutions with just 5. A very good book that I suggest is Watkins, Across the Board, The Mathematics of Chessboard Problems. And one of the solutions out of this 4,860 is this. If you place this queen like this, either the queens are occupies the square or being attacked by someone in the squares. So 5 is minimum and 5 is the queen's domination number for 8 by 8 chessboard. This is another puzzle. Can you trace this? Anyone who has studied graph theory will be able to just look at vertices of odd degree and count the possible number of paths. Whether I can trace this or not trace it is a typical question in what is called unicursal graphs. So graph theory is related, as mentioned earlier, groups, vector spaces, page rank algorithms, lattices, number theory, combinatorics, design theory, chemical graph theory, phylogeny, epidemiology, algebra, and all these things. It is highly interdisciplinary topic. And definitely the phylogenetic tree, the concept of an acyclic connected graph, which was introduced by Arthur Cayley, is now being applied in phylogeny also. So we feel that biology is more of mathematics because we are using several mathematical terms to analyze the biological structures. So what you know by what I mean by phylogeny is the history of the evolution of a species or group, especially in reference to the lines of descent and relationship among broad groups of organisms. In medicine, phylogenies have been used to trace the origins and transmission rates of infectious diseases, including AIDS, dengue fever, and SARS-CoV-2. So there are several books on this. The beautiful book by Bapat on graphs and matrices, first course in graph theory and combinatorics by Sebastian Sioaba and Ramurthy. This is a book by Van Lind and Wilson, and plenty of books are there. So what we see as the graph in the textbooks is an abstract static graph in the sense that the graph's vertices and edges are not changing. Several years ago also, as this Peterson graph had 10 vertices and 15 edges. So these are all examples of static graphs, which we are going to discuss first. I will talk about one property of Peterson graph, that it's an example of a unit distance graph, a concept in geometric graph theory. A unit distance graph is a graph formed from a collection of points in the Euclidean plane by connecting 2 points by an edge whenever the distance between the 2 points is exactly 1. So the points that you take are points in the Euclidean plane R2, and I'm going to join these points by an edge if and only if their distance, Euclidean distance is 1. You see that they are not always planar. If this unit distance graph is planar, it's called a matchstick graph. You can Google and get more results on matchstick graph. And you can easily see that the non-planar graph, the Peterson graph, is also a unit distance graph. And this is the drawing of the Peterson graph where any 2 points are of unique distance. Okay. As I told you in the beginning, I will be focusing more on popular problems and Indian contributions. So let me talk about perfect graphs. A perfect graph is a graph in which the chromatic number and the clicked number, the largest click of the sub, is equal for every induced subgraph. So for every induced subgraph H of a graph G, chi H is equal to omega H, chromatic number is equal to click number. There is a very big, huge graph classes which are perfect. Bipartite graphs, line graphs of bipartite graphs, caudal graphs, split graphs, interval graphs, and so on. They are all perfect. What is interesting for us is a conjecture which was posed by Claude Berge in 1962 when he was visiting Indian Statistical Institute, Kolkata. This is the great Berge with Paul Erdős. He has two books, one on theory of graphs and theory of hypergraphs, which discusses the celebrated strong perfect graph conjecture. Let me also take you to congratulate Laszlo Lovász, good friend of Cochin and good friend of many of us, and Abela Wright in 2021, because he has a contribution to the solution of strong perfect graph conjecture. The strong perfect graph conjecture of Berge says that a graph is perfect if and only if it does not contain an odd whole, that is C2k plus 1, or its complement. This version of strong perfect graph conjecture was possible because of an intermediate theorem that Lovász proved in 1973, that a graph is perfect if and only if its complement is also perfect. So that was the role of Lovász to bridge a gap, to fill the gap between the 1961 strong perfect graph conjecture and 2002 strong perfect graph theorem by four mathematicians, Maria Chudnowsky, Neil Robertson, Paul Seymour, and Robin Thomas. Robin Thomas, I had the opportunity to interact with him. Unfortunately, he passed away 2 years ago. Incidentally, he was the doctoral student of Jaroslav Nesetril, whom many of us know. This is great Paul Erdős. I was fortunate enough to meet him in his office in Budapest. So this is a humble tribute to Paul Erdős, who passed away in 1996. So I will spend about 10 minutes to talk about Srikhande and his work and his graph. A great Indian mathematician, graph theorist, and design theorist who lived during 19th October 1917 and 21st April 2020. He passed away at the age of 102. And what Srikhande did is can be explained in just 2-3 slides. He made a great breakthrough in a conjecture of Euler, which he posed in 1782, what we call as a solution to the 36 officers problem. Or put it in Latin squares point of view, can you find a pair of mutually orthogonal Latin square for every n of the form 4k plus 2? This was a conjecture posed by Euler in 1782, which was disproved completely by a team of mathematicians popularly known as Euler-Spoiler, R.C. Bose, Esther Srikhande, and E.T. Parker, proved that there exist pairs of n by n mutually orthogonal Latin squares for all n except n is equal to 2 and 6, totally saying that Euler was completely false, and which came as a paper in the Transactions of American Mathematical Society and Canadian Journal of Mathematics in 1960. And this is great Srikhande, and this is R.C. Bose, this is Parker, as I said, popularly known as Euler-Spoiler. This is, according to me, the first newspaper report of any mathematical activity all over the world. I may be corrected. I've told this in several international forums, that this is about the solution of the Euler's conjecture by R.C. Bose, Srikhande, and Parker. So this is the beautiful Srikhande graph. I am going to spend some time on this because this is an example of a strongly regular graph. Strongly regular graph is actually an indigenous Indian product due to R.C. Bose in 1963 and also Professor Srikhande. So let me define what is a strongly regular graph with parameters n, k, lambda, mu. It's a graph with n vertices. Every vertex is of degree k, regularity is k. So every vertex has k neighbors. And any two adjacent vertices have lambda common neighbors, and any two non-adjacent vertices have mu common neighbors. So these are the parameters of a strongly regular graph. You can see that our Srikhande graph is a strongly regular graph with the parameters 16, 6, 2, and 2. So any two adjacent vertices have two common neighbors means at least one, if there is one common neighbor, you get a triangle. And any two non-adjacent vertices have two common neighbors. And in general, nk, lambda, mu is what are called the parameters of a strongly regular graph. Let me remind you that it cannot be lavishly independent. They are strongly connected. These parameters are connected, so we cannot have full freedom to choose these parameters. To introduce the origin of Srikhanda graph, I have to talk about an L2M graph, where M is the set 1, 2, 3, etc. M, and vertex set is M cross M, and two vertices are adjacent if the first coordinate or second coordinates are same. This is precisely the graph on the cells of M by M chessboard, where two cells are adjacent if they are in the same row or column. I hope the definition is clear. I say that two vertices represented by the cells of an M by M chessboard are adjacent. They are made adjacent, provided they lie in the same row or column. And you can easily see that by actual counting that this L2M graph is actually a strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, and 2. Here comes the celebrated Srikhanda theorem that whether the parameters are unique for Srikhanda graph, and there is a beautiful result of Srikhanda which says that if G is an SRG, strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, and 2, then G is isomorphic to the lattice square graph L2M, except when M is equal to 4. So when M is equal to 4, you know the parameters become 16, 6, 2, and 2. And that exceptional graph is the beautiful graph which I showed you earlier, the Srikhanda graph. So except for M is equal to 4, the strongly regular graph with parameters M square, 2 into M minus 1, M minus 2, and 2 is uniquely determined by L2M. I'll focus more on algebraic graph theory. You know, algebraic graph theory deals with the blending of linear algebra and graph theory. So broadly, we say that algebraic graph theory deals with three topics. One is use of linear algebra and spectral graph theory, use of group theory in K-Lie graphs and zero devices graph that my friend Tamiselvam is going to talk, and the theory of graph polynomials, where you are worried about the solution set, roots of the polynomial, like characteristic polynomial, chromatic polynomial, independent polynomial, matching polynomial, and such things. So broadly, algebraic graph theory touches these three areas. So I'm going to say something more on the adjacency matrix of the strongly regular graph. A strongly regular graph with adjacency matrix, a regular graph with adjacency matrix A is strongly regular if and only if they satisfy the two conditions, Aj is equal to Ja is equal to Kj. So Aj is equal to Kj means K, the regularity will be an eigenvalue, and there are two more eigenvalues which you are going to show, and satisfies the equation A square plus mu minus lambda into A plus mu minus K into I is equal to mu G. So this is the adjacency matrix characterization of a strongly regular graph, which makes us possible to say that any strongly regular graph has only three eigenvalues, and any regular graph with the three eigenvalues has to be a strongly regular graph. So apart from the regularity K is the maximum eigenvalue possible thanks to the Perron-Frobenius theorem. The other two eigenvalues are 1 by 2 into lambda minus mu plus or minus root of lambda minus mu whole square plus 4 into K minus mu lambda. Consequently, it is easy to find the eigenvalues of some well-known graphs because they are all strongly regular. So let me take a second, pause for a second, that a graph is strongly regular if and only if it has got three eigenvalues, if and only if the characteristic, the matrix satisfies those two conditions. Therefore, I can find the eigenvalues of strongly regular graph, the Peterson graph, which is 10, 3, 0, 1. The eigenvalues are 3, 1, minus 2. Srikhanda graph is also strongly regular, therefore its eigenvalues are 6, 2, minus 2. And the famous Klebsch graph, which I have drawn here, eigenvalues are 5, 1, minus 3. And strongly regular graph, which is of that of Hoffman-Singleton graph, which I showed earlier, with the parameters 5701 is 72 minus 3, thanks to the characterization of eigenvalues of a strongly related graph. Otherwise, you have to solve a characterization of which is a polynomial of degree 50, which is not a joke. There are two interesting problems which are still open in strongly irregular graphs. One is due to John Conway, a celebrated English mathematician who passed away due to COVID in 2020, 11th April. This problem is what is called Conway's 99 graph problem, is to construct a strongly irregular graph with parameters 99, 14, 1, and 2. You may think that it is easy, but it is still an open problem due to John Conway. Another problem is about Moore graph. Moore graph is a strongly irregular graph with lambda is equal to 0. Lambda is equal to 0 means any two adjacent vertices have no common neighbor, therefore there are no triangles. It is triangle free. And any two non-adjacent vertices have exactly one common neighbor. So mu is equal to 1. Because there is no triangle, the girth is going to be 5. So precisely, Moore graphs are strongly irregular graphs with lambda is equal to 0 and mu is equal to 1 and girth 5. Due to Edward F. Moore, who is an American computer scientist, inventor of the Moore finite state machine. What is interesting is there are only 3 non-Moore graphs: the cycle C5, the Peterson graph, and the Hoffman-Singleton graph. And a great problem is whether the Moore graph with parameters 32, 50, 57, 0, and 1 is the only possible parameters for which a Moore graph could exist. Believe me, even up to 2021, this result is open because it is still unknown even now if such graph exists. That is, does there exist a Moore graph with parameters 32, 50, 57, 0, 1? Mind you, the graph is having 3,250 vertices and the regularity 57. Therefore, number of edges is going to be 92,625. So it's an open problem whether the Moore graph, fourth possible Moore graph, exists or not. So Euler, this Sriganday graph is not uniquely determined by its spectrum. In fact, it's an integral graph. It's Eulerian. Chromatic number is 4. Girth is 3. It is Hamiltonian. It is edge connectivity is 6. Independence number is 4. It's strongly irregular with lambda is equal to mu is equal to 2. So therefore, it comes as a graph associated with a symmetric, balanced, incomplete block design. It's a Cayley graph, whereas Peterson graph, which is strongly irregular, is not a Cayley graph. It is not planar, but it can be embedded in a torus. We still don't know what is its chromatic polynomial, number of different ways of coloring the graph using lambda colors. But we know that the automorphism group of Peterson graph, Sriganday graph is of order 192, but the proof is not that trivial. Okay. Let me go to another Indian who has become very, very famous these days. To talk about that person, of course, Ramanujan name comes here. You have to talk about, in just 2 slides, Ramanujan graph. Let A be the adjacency matrix of an undirected graph G. You can easily see that the maximum eigenvalue possible is upper bounded by the maximum degree, obviously. So if it's a k-regular graph, mod lambda is less than or equal to k. So all the eigenvalues are going to lie between minus k and k. So this is the ordering of the eigenvalues. And if you denote by lambda, the maximum modulus of eigenvalues other than k, I'm going to leave k. So next largest eigenvalue is denoted by k. And I said that a graph is Ramanujan if it is a k-regular graph satisfying lambda g is less than or equal to 2 root k minus 1. I'm not going to spend time on why this is called Ramanujan graph. Anyone who is interested in this origin of the terminology, you just Google Ramanujan graph. You'll get a beautiful article by Ram Murthy on this and Sebastian Sioba. You can get more information. So let me focus here that the maximum, a graph is Ramanujan if its maximum modulus of the eigenvalue other than the regularity satisfies less than or equal to 2 root k minus 1. You can give some simple examples of Ramanujan graph, complete graph of order d plus 1, degree regularity d plus 1 has eigenvalues d and minus 1. And you can see that lambda of kd plus 1 is 1, which is less than 2 root k minus 1. Complete bipartite graph KRR, because it is bipartite, whenever R is an eigenvalue, minus R is also an eigenvalue. So spec is R0 minus R. So it is also a Ramanujan graph for every R, satisfies the inequality. Peterson graph is an example of a 3-regular Ramanujan graph. And if you want infinite family of Ramanujan graphs, you get out of Pali graph of order cube, which can be used to design a strongly regular graph. But what is interesting and surprising to know is that a team of mathematicians, Adam Marcus, Daniel Spielman, and Nikhil Srivastava. Nikhil Srivastava was a speaker in the last offline Ramanujan Mathematical Society conference held in Pondicherry, proved the existence of infinitely many deregular bipartite Ramanujan graphs for d greater than or equal to 3. It was a very, very, very innovative and hard method of interlacing polynomials, which he used to get this characterization theorem. Let me show you Nikhil Srivastava. He is an Indian-born American mathematician who is a professor in University of California, Berkeley, who got George Polya Prize of Siam in 2014. Michael and Shaila held prize in 2021, and the first Cyprian Foyes Prize in 2022, which was announced last month. So, salute Nikhil Srivastava. Now, I need only some 5 to 10 minutes to conclude. I am moving to the modern applications of graph theory. So far, we were discussing with abstract static graphs, which do not change at all. But the graphs that you find applications nowadays form under the huge category called real-world networks. So they are all dynamic in the sense that vertices and edges are going to change every second or even fraction of a second. So these are all some examples of dynamic networks. So there, I have a simple situation. When my friend Chirag invited me to this conference, I made a Google search of Hemachandra Acharya, North Gujarat University. And poor Google is a search engine. I gave the keyword Hemachandra Acharya, North Gujarat University. And what the Google did was to produce 290,000 results in about just 0.48 seconds. My questions to my young junior friends that are attending this presentation is, how could Google calculate or give this much number of results just taking 0.48 seconds? Let me very proudly tell you that Google could tell from this database in about just 0.48 seconds that there are a lot of information about HNGU in the website. And in fact, what all that I wanted to know was when this university was established and all that. Okay, right. So how does Google Google? The mathematics behind the internet is just linear algebra. I don't say just linear algebra. You have to solve, or you have to find the characteristic roots or eigenvalues of a matrix which is 80 billion by 80 billion. That is 64 into 10 raised to 14. Using the wonderful PageRank algorithm, it's all easy now due to Larry Page, who is also an ex-CEO of Google, and he's also an ex-CEO of Alphabet company. This is Larry Page. And the mathematics or graph theory behind it is what's called the PageRank algorithm, or the matrix, what is called the adjacency matrix of the website, what is called the Google matrix. So a Google matrix is a particular stochastic matrix. Stochastic means the entries are probability, therefore their row sum or column sum add up to 1. And that beautiful matrix is used by Google's PageRank algorithm to tell you that that much number of results are there in the Google. The matrix is the adjacency matrix of a graph with edges representing the links between the web pages. The basic principle governing the PageRank algorithm, and the reason why we are getting these values quickly is that the degree distribution of the various websites follow a power law. I'm not going to the, I may talk about this towards the end of my talk. So there is a new mathematics that has come up, what is called the Facebook mathematics. Facebook believes in the principle that friend of a friend of a friend of a friend is a friend. Now, all the 70 or 80 participants that now are attending this presentation is a friend of mine through Chirag Barsara, Samir Vaidya, Tamil Selvam, Mukti Acharya, who are all known friends of mine. But let me tell you that in 2020, there were 2.570 billion monthly active users for the Facebook. Therefore, the Facebook network is going to be very, very, very complicated and complex. Epidemiology and network theory gets related through graph theory. It is the most recent application of network theory or graph theory. And I will take only 5 minutes. Real world networks, I have to talk about real world networks in a broad sense. It is massive, huge, with billions and billions of vertices. It's complex, but they have a very nice property that it is sparse in the sense that the number of edges is going to be very, very small when compared to the number of vertices. That means the matrix, adjacency matrix, is going to have more zeros than ones because we are not going to get it connected directly, but we are going to get it connected through friend of a friend of a friend of a rule. Okay, so it is sparse matrix. And another thing is what's called, they follow the small world phenomena that any two vertices are connected by a shortest path. Two of the members need not be a friend, but I can always connect it through a chain of friends. So this phenomena due to Duncan Watts and Strogatz is 1998, and this is what's called the small world phenomena. As I said, the degree distribution satisfies power law. That is, if you say that nkj is the number of vertices of the graph with the degree k, that nkg satisfies a power law. That is, if you take logarithm, log nkg is log n minus beta log k. This is of the form y is equal to mx plus c. Therefore, log plot of this power law will be a straight line with the slope minus beta. And this beta is going to be the villain because determining beta is not a joke. And therefore, we have a wonderful result of Barabasi and Albert that the diameter of the World Wide Web is just 2.1. It appeared in a celebrated paper of him in 1999 in Nature. So this is basically the power law distribution, and this is basically the Bayesian distribution of or what called bell curve distribution. And in power law distribution, very many nodes with only a few links that I told you that it's going to be a sparse matrix, and a few hubs with large number of links. Hubs means all people are going there. Okay, so that is the structure of the power law distribution. And our biological networks are follows power law. Protein interaction networks follows the power law. And there are many networks like brain network, World Wide Web, which also follows power law. But they broadly come under the category of scale-free networks. If the characteristics of the network are independent of the size of the network, that means that when the network grows, the underlying structure remains the same. There is a beautiful theory which says that there is a 6 degrees of separation between any two human beings. That is, everyone is at most 6 steps away from any other person on Earth because we are going to have the small world property. And it has been proved by a team of scientists in Microsoft and Facebook that the Facebook degree of separation is just 3.57, not 6, because of the density and contact density of the members of the Facebook. Okay, so Facebook claims that there are only 3.57 degree of separation between people, not 6 as thought of earlier. So Facebook, an example where every person gets connected to every other person. Okay, one more point and I will stop. Graph theory has reached a stage where it is going to explain the theory of natural selection and the origin of species given by great Charles Darwin. And that has resulted in the formation of a new graph theory, new branch of graph theory called evolutionary graph theory, mainly due to the mathematical biologist Martin Nowak, who is director of the program for evolutionary dynamics in in the Harvard University. He thinks that the graph theory tools can be better used for finding solutions to evolutionary dynamics and principle of natural selection. So I conclude with the warning that www is an infinite imaginary library. According to 2019 statistics, it is 1.94 billion vertices are there. So that is 1.94 into 10 raised to 9. Why should we worry about this is that the mathematics is going to be more complex. We may need more new mathematics, a new interdisciplinary approach. So let us all join hands to build up new mathematics to explain new phenomena that is likely to come up. So let me stop with the social message that we should break the chain, and welcome to Cochin after pandemic. Thank you all, my dear friends, and Chirag Barsara and Professor Samir Vaidya for involving me in this deliberation. And thank you very much, and thank you.
Thank you, Dr. Vijay Kumar. Dr. Vijay Kumar has covered all the applications ranging from biotechnology and all the fields of life science and the networks. It was a very wonderful talk, and for the budding researcher, it will create the curiosity. Only one or two questions I will like to allow, looking to the crunch of time. If anyone have any curious question, then they are welcome. They are allowed to unmute themselves and ask the question to Professor A. Vijay Kumar.
Professor Vijay Kumar, just I would like to know, somewhere else you have observed that Peterson graph is not Cayley, whereas a streak and a graph is a Cayley graph, isn't it?
Yes.
What is the corresponding group? Whether it is D16 or Z16 or something else? Because it is a group.
I have to refer. I will tell you.
Yeah.
I will tell you. Definitely tell you. You mean you want to know what is the group that you are getting?
In the case of Peterson graph, in the case of Peterson graph, it is a group of order 10.
Yes.
Neither for a D10 nor for Z10, the corresponding regularity property is enjoyed. Thereby, it has been disposed of.
Yes.
What is in the other case? Just out of curiosity.
I will tell you. I will tell you.
Yeah, it's not a just I want.
I will tell you.
Any other questions, comments?
And let me tell you for the audience that if you want to construct any R-regular graph, the Cayley graph technique is the best. It is used in the construction of very large scale interconnection networks.
Just it is 16 parameter something. What is the parameter for streak and a graph?
16,622.
Yeah, it is 16,6. So there must be a group of order 16 and a generating set of order 6. Yeah. Okay. Fine.
So thank you.
My email ID. Those who want to interact with me can do it through email.
Yeah. So thank you, Professor Vijay Kumar, for being with us, and you have graced the occasion. So on behalf of organizing committee, I am very much thankful. Thank you. Today's next speaker is Professor T. Tamish Shalmo. I welcome you, sir. Professor Tamish Shalmo has worked on various academic as well as administrative positions. He has worked as a registrar of the Manamanyam Sundarnath University with his regular duties and post of head of the Department of Mathematics at Manamanyam Sundarnath University. Presently, he is working in the same university as CSIR Emeritus Scientist and at Manamanyam Sundara University, Tirunelveli, Tamil Nadu. He has also visited abroad countries like UAE, Malaysia, Hungary, Taiwan. He has published 11 books and more than 150 research papers. Popularity of his publications can be known with I-10 index 33 and H index 20. He has guided 26 PhD students and co-guided 20 students, while he has supervised 50 students for MPhil dissertations. We are lucky enough to have such eminent graph theorists on this virtual platform. I welcome you, sir, and request you to deliver your talk entitled as Trace Graph of Matrices over a Commutative Ring. Dr. Kamish Chalman.
Good afternoon to everybody. I am very much thankful to Professor Vaitya as well as Dr. Chirag Barasara for this opportunity of interaction with the young mathematicians as well as the discrete mathematicians of this nation. Today my topic relates, because of the time constraint, I feel that just straight away I get into my topic. Today the title of or the content of my talk relates to two vital disciplines of mathematics, namely algebra and graph theory. More specifically, I would like to draw the attention of young researchers, the interaction between the matrices and the graph constructions. Just let me share the it is start broadcast or screen broadcast. What is the?
You need to share the screen.
Share the screen and
share
then
entire screen.
But I am getting only screen broadcast, WebEx Meet, start broadcast.
On share, you are getting screen one, suppose like that. We have, yes, sir.
I am getting the three things: screen broadcast.
Sir, now your screen is visible to us.
Okay.
Just click on the backside. Yes, it is now visible to us.
Do you see my presentation?
Yes, sir.
Yes.
Yes.
Yeah. Now,
Okay. Fine.
slides are visible.
Okay, fine. Okay. So the today topic is trace graph of matrices over commutative rings.
Can you zoom it, sir? Full page?
Madam?
Your screen is very, what happens, small. That.
No, I am getting full screen.
Oh, you are getting full screen, but here I don't have full screen.
Madam, you select from the layout side by side or stick.
Yeah, that may be.
Okay.
Okay. Thank you. Of course, just I would like to draw the attention of the people that the very first graph construction from an algebraic structure start from the construction of Kelly graphs in 1878 by Arthur Kelly. Of course, the title of the paper was Pictorial Representation of Finite Groups, appeared in Journal of American Mathematical Society, Volume 2, the very first paper. Of course, even though the construction was in 1878, in late 1960s, due to its varied applications in parallel computing, it has attracted many people and it has been the point of study in the perception of parallel computing, especially the Kelly graphs, which are having the very fundamental property of regular and vertex transitive. Those two properties put it in the front line in supplying the tools for routing problems. Of course, thereafter it was technically studied. In fact, in the perception of this decomposition problem, this Kelly graphs have got bigger role. Of course, in 1988, another very big construction or very notable construction has been done in the perception of graphs from algebraic structures, namely zero divisor graphs by Ivan Beck and subsequently by Anderson and Livingston in 1992. Of course, there are very many constructions on commutative rings. At least if I happen to know about 40 graph constructions from commutative rings. Any interested reader can refer our recently published book in December 2021, Graphs from Rings by Springer Nature. Of course, there are Kelly graphs from commutative rings also, and one of the advantage of doing Kelly graphs from commutative rings, when the Kelly graph is being considered as a graph from finite group, finding automorphism group was a much more complicated problem. Rather, in the case of Zn, the congruent modulo n classes, finding the automorphism group was much more easy when the ring theoretical tool was employed. Of course, there are some graph constructions from non-commutative rings. In fact, my talk stands in that category. The content relates to the graph construction from non-commutative rings, which is started in the year 2019, and it is very, very recently happened. Of course, there are graphs from semigroups, there are graphs from lattices, posets, vector spaces, and so on. In fact, module theory, the very recent activity in the domain of graphs from commutative rings is in the generalized perception, and more specifically, the graphs from modules are taken care of a very generalized framework for these structures. Of course, just these are all the notations I will be making use of. R is a commutative ring with identity. Z of R is a set of all zero divisors of R. Of course, the elements enjoying the property AB equal to 0, A and B are elements of R. Z star of R denotes non-zero zero divisors of R. And nilpotent is the set of all nilpotent elements which are subset of the zero divisor set. And in a commutative ring, the complement of zero divisors is referred as regular, even though it is little bit deviation from the notion of regular elements by von Neumann, a very famous regular element definition. And U of R denotes the set of all units of R. And of course, just let me recall the definition of the zero divisor graph by Ivan Beck in 1988, Journal of Algebra. Of course, this is not the definition exactly given by Ivan Beck. It is the definition given by Anderson and Livingston. Anderson is the one of the co-author of our book. It is a four-author book. Let R be a commutative ring. The zero divisor graph denoted by gamma of R is the graph with the vertex set Z star of R, that is non-zero zero divisors, and two elements are joined, two distinct vertices are joined, provided their product is zero. So in this part of graph theory, normally people used to take either the whole of the elements or a subset of elements as the vertex set, and always the edges are created through some algebraic property. Of course, the thing which is being used in the case of zero divisor graph is nothing but the product is zero. Of course, one can see that the graph will be empty, the zero divisor graph will be empty if R is an integral domain and vice versa. And in the algebraic perception, the degree of any vertex in zero divisor graph is nothing but cardinality of or number of elements in the associate of that particular element minus 0 comma that element. If I take A, the degree of A in the zero divisor graph is nothing but cardinality of associate of A minus 0 comma A. 0 is the additive identity in the ring. Of course, just for the young people who have not come across this idea so far, just this example will give a fundamental idea. I consider here three rings. One is Z6, congruent modulo 6 classes with respect to addition modulo 6 and multiplication modulo 6. Of course, one can trivially verify that 2, 3, 4. Just I don't read 2 bar, 3 bar, 4 bar. Just I read 2, 3, 4. They are the zero divisors. Of course, 0 is not considered there. In the case of Z8, congruent modulo 6, 8 classes, 2, 4, 6. In the case of the polynomial ring, Z2 of x over x cube, the ring is Z2 of x, all polynomials in x with the coefficients in Z2 over the ideal generated by x cube. Of course, the zero divisors are nothing but cosets with coset representatives x, x square, x plus x square. Of course, for all these three rings, the zero divisor graph is nothing but P2, the path of length 2, because you can take this particular first element as 2, this as 3, this as 4 in the case of Z6. In the case of this ring, you can take this is 2, 3, 4, and of course you can verify that 2 into 3, 6, 0 joined, 3 into 4, 12, 0 joined, and ultimately this is a zero divisor graph. In the case of Z8, this is 2, 4, 6. In the case of the quotient ring, this is x square, this is x plus x square. Of course, this simultaneously conveys a very strong property that these are all three commutative rings which are not isomorphic as rings. Very trivial observation is the first one contains 6 elements, the second one contains 8 elements. There is no possibility of an isomorphism, but the derived graph is only one, the zero divisor graph. So non-isomorphic rings may create the same zero divisor graph. Of course, it is because of the reason that the zero divisor part only being taken into consideration for the construction. That is why it is not fully representing the algebraic structure. Of course, what I would like to draw to the audience is that the converse problem is complicated problem because of this. So given graph, can you find one commutative ring for which this is isomorphic to the given graph? That's a very complicated problem. Okay. Of course, right from 1988 to till date, the zero divisor graph is very hectically studied. There are umpteen number of papers appeared on this particular topic. That's okay. And this trace graph of matrices, this is a concept which is being introduced in 2019. Of course, R is a commutative ring. I consider Mn of R, the set of all n by n matrices over R, n is greater than or equal to 2. Why I consider n is greater than or equal to 2? In the case of n is equal to 1, this Mn of R is nothing but R, and just you will realize that after 2 slides or maybe in the next slide, you will realize that the trace graph corresponding to 1 by 1 matrices is nothing but zero divisor graph. However, at this point, just I would like to recall certain facts about matrices and graph constructions. Bosick and Petrovic in 2014, they investigated the zero divisor graph of matrices. Of course, as I said in the beginning, zero divisor graph of non-commutative rings drawn the attention of the researchers right from 2002 by Redmond and subsequently by many other authors. And these people, these two authors, they have concentrated on matrices. More specifically, they have taken set of all n by n matrices and they have considered the zero divisor graph of those matrices. Especially, they have determined the diameter and breadth of the zero divisor graph of matrices. Of course, this study on the ring of matrices attracted many. Not only attracted many, it is the fundamental tool for the unsolved part of the game still, because the zero divisor graph for non-commutative rings are not well studied because of the complication. And I feel that the only tool to attack the class of non-commutative rings can be only through the ring of matrices because of the Artin semi-simple theorem. Of course, in 2018, Al-Magdi et al., they introduced the concept of trace graph of matrices that has appeared in Acta Mathematica Hungarica by Springer. Just let me introduce the zero divisor graph. Throughout my talk, this TR of A denotes trace of the matrix A. A is a square matrix. You can sum all the elements in the main diagonal, and that is called trace of the matrix. Of course, as I said, Mn of R denotes the set of all n by n matrices. The trace graph of Mn of R is denoted by gamma T of Mn of R. And the vertex set is, please look into the fact, the vertex set of this graph is nothing but set of all non-zero n by n matrices such that there exists at least one non-zero n by n matrix over that ring R such that trace of AB equal to C. A into B is the product of two n by n matrices. Their sum of diagonal elements must be 0. Of course, we consider only distinct because we wanted to have a simple graph. And this is the trace graph. And the very purpose of taking the vertex set as this way reveals that for every A, there exists at least one B such that trace is 0. So we have they have completely avoided the isolated vertices. Suppose there exists no matrix with this property that is not being taken in the vertex set. That doesn't mean that the graph is connected. The graph may be disconnected. However, we are avoiding isolated vertices. Okay. Before, when n is equal to 0, this A and B become entries of commutative ring R. This trace of a single matrix is nothing but the same one. Therefore, it is product is 0. Ultimately, trace graph is nothing but zero divisor graph when n is equal to 1. So when a study is being attempted on the trace graph of matrices, naturally, we need not consider zero divisor graph. Thereby, people started doing the business only for n greater than or equal to 2 in this part of the mathematics. And please note that as mentioned by Professor Vijay Kumar, this dense graphs play vital role in graph theory. Of course, almost all of the graphs constructions from commutative rings, the diameter is less than or equal to 3. If my memory is correct, except in the case of Jacobson graph, this fact happened to In the case of Jacobson graph, the diameter is less than or equal to 4. So in the sense that this diameter less than or equal to 3 means every third vertex, you have to come back. You cannot go beyond that. And of course, in the case of trace graph, you cannot draw the graph just like that, because even for M2 of Z2, there are 16 vertices. You cannot draw the graph. So just I have drawn the induced subgraph induced by 2 by 2 matrices over Z2 with non-zero trace value. Okay. So this is the 8 matrices. If you take these 2 matrices, edge has been drawn. If you multiply these 2 matrices, you will realize that you will get only 0. Yeah, it is a trace value is 0. Therefore, they are joined. And similarly, you can attempt these things. Yeah. You see, this is not the trace graph of all 2 by 2 matrices over Z2. It is only an induced subgraph of that subgraph. This contains 8 vertices only. There are 8 more vertices, and it is very dense graph. And of course, I am not able to induct the figure in this slide because it is drawn in a very big shape. So what is the fact I would like to draw to the audience is that this trace graph, you cannot observe anything after drawing the graph. Even for the simplest case, it starts with 16 vertices and so on and so forth. Okay. And of course, Almagadi et al., when they introduced this trace graph, they have first started studying about connectivity. Of course, it has been proved that the trace graph is connected. The diameter is 2, width is 3. In fact, that itself shows that the graph is very dense, because a general bound for known diameter is twice diameter plus 1. In that case, width is less than or equal to 5. But however, it is attaining the least possible value of width equal to 3. And not only that, for any graph, the special interest for the people will be what is the degree of the vertices. Suppose R is finite. Of course, I am reminded of the fact that in this part of the graph theory, we not only consider finite rings, we also consider infinite rings. Consequently, not only we consider finite graphs, we also consider infinite cases. So it is not my attention here. There are examples of infinite graphs from infinite rings. And suppose R is finite, then for a n by n matrix, I of A denotes this is nothing but sum of all elements of this kind R into Aij. Aij is the ijth element of A, and you have to make this sum that is denoted by I of A. And the degree of A is nothing but cardinality of R to the power n square by a cardinality of I of A, this set minus 1 if trace of A square is non-zero. In the case of trace square equal to 0, this number happened to be, or this degree, this parameter happened to be cardinality of R to the power n square by cardinality of I of A minus 2. Of course, one more, the induced observation here is the degree is either x or x minus 1. So if I take this top number as x, the second case is x minus 1. Therefore, thereby this trace graph happened to be biregular. Okay. And it has been proved that the minimum degree of the trace graph is nothing but cardinality of R to the power n square minus 1 minus 2. The maximum degree is ultimately known. And for the case of finite field, the maximum degree is cardinality of f to the power n square minus 1, and it is biregular. Sorry, I have to withdraw my statement. In this case, it is not biregular. It is only in the case of field, because the denominator may vary. But in the case of field, this happens to be, I of A happens to be the same number. Thereby, In the case of field only, the maximum degree is this one. And in the case of field, the trace graph happen to be biregular, not in the case of a general commutative ring. And there is a concept called irregularity index of a graph. You know the famous degree sequence for any graph, the set of all numbers which happen to be degree of vertices in the graph. This T of this trace graph is nothing but number of distinct terms in the degree sequence of the graph. So what is the irregularity index of the trace graph? In a simple terminology, for a regular graph, the irregularity index is 1, because all the vertex degrees happen to be the same. In that case, the irregularity index is 1. In the case of a biregular graph, the irregularity index is 2. And people, the authors who have introduced this concept of trace graph, first they have studied about irregularity index of this trace graph. Of course, they have beautifully proved that the trace graph of, the irregularity index of the trace graph is 2 if and only if R is a field. So that has been proved, because that set the category that the trace graph is biregular only corresponding to fields. In the case of non-fields, it is definitely, at least there are three integers which are happen to be the degrees of the corresponding trace graph. So natural question arises is 2 has been categorized. It doesn't happen. There is no case of regular trace graph. 2 is completely characterized, and people naturally interested in what will be the case of 3, or what is the characterization for the trace graph or the underlying commutative ring for which the irregularity index of the trace graph is 3. It has been observed that, it has been proved that the following are equivalent. The irregularity index is 3. R is a local ring with exactly one maximal ideal, not only a maximal ideal, only one non-trivial ideal. Local ring means it is a ring with a unique maximal ideal. It is something more here. R is a local ring with exactly one non-trivial ideal, and R is isomorphic to one of the rings in the 2 classes. One is ZP of xy. This is set of all polynomials in 2 variables x and y over the finite field of order P, and it is a quotient ring over Z of x comma y square. And another class is ZP square of x over Z of x plus P into h of x, where P is a prime integer. G of x is a monic irreducible polynomial in ZP of x, and degree of h of x is less than degree of g of x. So it's a complete characterization for the irregularity index 3. Of course, not only the characterization, they have gone into further. The irregularity index has been completely determined, and please note that suppose R is a commutative ring, I is an ideal. We determine one parameter called mu of phi. It is nothing but minimal number of generators for this ideal, and d of R is equal to maximum among all ideals of R. R is a commutative ring. I take an ideal. Mu of I is the minimal number of generators for I. Among all the ideals, I take the maximum one, that is called d of R. If d of R is less than or equal to n into n minus 1 by 2, then the list of vertex degrees of gamma t of mn of R is cardinality of R to the power n square by cardinality of I minus 2, or cardinality of R to the power n square by cardinality of j minus 1, where I ranges all the non-zero ideals of R and j ranges all the non-zero ideals of R. So it is in a way, it is algebraic characterization which gives the degrees of all the vertices in that particular trace graph. Using that, the irregularity index has been completely characterized. Of course, this is the last characterization. T is equal to T of the trace graph is nothing but Mn of R, which is equal to 2 into 2 times cardinality of I. I is a non-zero ideal of R. Of course, using which some more special cases has been done, that is there. Okay. So, in my perception or actual fact is the irregularity index of the trace graph of commutative rings has been completely characterized for all the cases. Okay. And eccentricity, naturally, once you know the degree, once you know the diameter and breadth, people are interested in distance, the eccentricity of a graph, and this is known. The eccentricity of every vertex of the trace graph is only 2. So that is what I said, you know, it's a very dense graph, the eccentricity is 2. Okay, this is the very first paper which appeared in Acta Mathematica Hungarica. I happen to know the paper through refining process, and we started working 2019. Some more graph theoretical properties of this particular graph, because we are already interested in non-commutative case of zero divisor graph of non-commutative rings. So in that perception, once we happen to know this, we started doing graph theoretical part of this trace graph. Of course, we have proved that it is not only connected, this trace graph is 2 connected. And the edge connectivity of the trace graph is nothing but cardinality of R to the power n square minus 1 minus 2. And in fact, why we are, as I said, our interest is always in the Artin semisimple theorem. Every non-commutative ring is isomorphic to direct product of the ring of matrices over integral domains. But that one component may correspond to matrices of order n1, another component may correspond to matrices of order n2. That's a complicated part. Still, the problem is very complicated. In fact, when the matrix orders are same, we have attempted some problem very quickly. Okay. So we are interested in comparing 2 trace graphs over the same commutative ring. One is corresponding to order n1, another one is corresponding to order n2. Naturally, n1 is less than or equal to n2. For 2 positive digits, n1 and n2, n1 less than or equal to n2, gamma t of mn1 of R is isomorphic to a subgraph of gamma t of mn2 of R. Of course, this trace graph contains at least one vertex of odd degree. Immediately, my mind goes to Euler's theorem. So I can conclude that this graph is never happened to be Eulerian. But on the other hand, it enjoys a beautiful thing that it is sub-Eulerian. That is, for every subgraph, it happens to be Eulerian, and it happens to be super Eulerian also. So that's the it is not Eulerian for itself, but for the part of subgraph and supergraph, this happens to be Eulerian. And there is a cycle of length 3 in every trace graph, and this trace graph contains a cycle of length. In fact, this is a property with respect to pancyclic. There is a notion called pancyclic. Every vertex lies in a cycle of length k. K lies between 3 and n. N is the number of vertices. And we have proved that it is every vertex lies in a cycle of length 3. Every vertex lies in a cycle of length 4. Every edge lies in a 3 cycle, and so on. Of course, this is our main concern, because we are always interested in the direct products. Suppose R and S 2 commutative rings, n is a positive integer, the domination number of the trace graph of n by n matrices over R cross S, the direct product of R and S, is the minimum of the domination numbers of the individual trace graphs. Individual in the sense that this is the trace graph of R, this is trace graph of S. And of course, that has been effectively used for general case also. And we have proved that in the case of R and S, if they happen to be the same Z2, not only Z2 cross Z2, Z2 times Z2 times Z2, m copies, then the domination number happened to be 3. That is domination of trace graph of n by n matrices of direct product of m copies of Z2. Okay. And of course, it is non-planar. Naturally, it must be the case because it is a very dense graph. Edges are more in number. And but the non-planarity is not the very beautiful observation. On the other hand, it has been observed that it cannot be toroidal, genus cannot be 2, but the minimum is nothing but genus is greater than or equal to 9. Of course, we have got good work on the genus of graphs from commutative rings. We have, for many classes, we have attempted planarity, toroidal, and so on and so forth. But such a study is not possible in the case of trace graph. Hello. Hello.
Hello, Tamaselvam.
Please.
Yeah, what did you say about the genus?
It is minimum 9.
Oh.
Minimum 9.
Okay.
You cannot even draw the embedding. The classical tools available as of now, you cannot draw a trace graph in a plane or surface, torus, and so on and so forth. It's very complicated. And you may ask that how do you find? It is just because of the minimum bounds available classical complete bipartite and complete graphs. So deriving the lower bound is very easy. But even the problem for what rings it is 9, I feel it is very complicated. I don't have any answer for that.
Okay.
And of course, for n greater than or equal to 3, if you drop 3 by 3 instead of 2 by 2 matrices, if I take 3 by 3 matrices, but the ring is only Z2 or is Z2, the genus happen to be greater than or equal to 4. Even in that case, it is complicated. Even 2 by 2 matrices, 3 by 3 matrices with at least over Z2. And of course, as in the case of ideal based zero divisor graph, not only in the case of zero divisor graph, for every algebraic graph, the things are generalized through ideal based. The concept is very simple. In the case of a zero divisor graph, 2 distinct vertices are joined provided their product is zero. Just you generalize that condition. Instead of taking product is 0, you take that the product must lie in an ideal. When the ideal happen to be 0, that comes to the case of zero divisor graph. When the ideal happen to be something else, it is a generalized ideal based zero divisor graph. In parallel to that, we have generalized the ideal based trace graph. The concept is very simple. For n greater than or equal to 3, I take an ideal I of R. The vertex set is nothing but I consider Mn of R minus Mn of I. This is the set of all matrices with the entries in I. This is a set of all matrices in R. I don't consider vertices in I because just the reason is 2 distinct matrices are adjacent provided the product of the trace is an element of I. So naturally, one can visualize the fact that if I take matrices with the entries in I, naturally the trace will also be there. It is an induced complete subgraph will be there. So we have to avoid that. That is why those vertices are not being considered. So this concept was generalized through this, and that also been well studied. And of course, it contains no isolated vertices. No vertex is adjacent to every other vertex. That means to say k1 comma n minus 1. Suppose G is a graph of order n, k1 comma n minus 1 is not a subgraph of that. That is what it meaning. And it is connected with the diameter to grid 3. And of course, the tool of generalization through ideal gives a much more sophisticated property that, or it is always the customary that. Even in the title, you can see first one is the trace graph of n by n matrices over R. The second one, this is the ideal based trace graph of n by n matrices over R. When I is equal to 0, this becomes the trace. So naturally, we are interested in doing, suppose I take two matrices here, what shall be the corresponding cosets? If the cosets are adjacent in this generalization, what will happen in the previous? Sorry, such relations have been discussed. I am not just reading them, but there are things. And what is the benefit of all these things is ultimately a beautiful decomposition has been done in the case of ideal based trace graph. That is, ideal based trace graph of Mn of R contains cardinality of Mn of I disjoint subgraphs. Each one is isomorphic to the ideal based the trace graph of the quotient ring R by I. Please look at that. Why? The ideal based trace graph of R with respect to I is isomorphic to, or it is nothing but cardinality of Mn of I disjoint subgraphs. Each one is isomorphic to trace graph of quotient ring R by I. And this has been effectively used. That is what being denoted here. Suppose R is a commutative ring with identity. I is a non-trivial ideal of R. N greater than or equal to be an integer. Let me take lambda equal to set of all cosets A bar, which is in the vertex set of trace graph of R by I, for which trace of A square is in I and A is the coset representative of A bar. Then this ideal based trace graph is isomorphic to the such a beautiful decomposition has been obtained, and that is no. Of course, we have studied about the chromatic number through this ideal based construction. Not only chromatic number, clique number, and because of that, it has been proved that this graph is weakly perfect. The chromatic number is equal to clique number for the ideal based trace graph. And we have some more properties with regard to domination, which I hope I have not included. And however, we have determined the independence number of this graph, and alpha has been determined through this trace of A square is an element or not, and it has been well studied. Once again, I would like to attract the attention of the audience that the properties of the graphs from matrices will definitely give a tool, effective tool to the zero divisor graph of non-commutative rings. So, and of course, we have considered the direct product with the orders of the matrices equal, but that will not help. One has to consider direct product of two matrix rings of different orders, and if the things have started, if someone starts in that direction, definitely it will be a breakthrough in the case of non-commutative or zero divisor graph. Not only zero divisor graph, for any other graph from commutative ring, from ring, it can be a 2. So these are all, and of course, this is our book just now published. Anderson, Asir, Badawi, and myself, Graphs from Rings, Springer Nature. And of course, these are the fundamental papers in this particular topic. Of course, a few more papers have been published. First one is an Acta Mathematica Angelica, second one is ACT Journal of Mathematics and Statistics, which is also an SCI journal. Of course, few more papers are there, which I have not given. If anybody is interested, you can send an email to me. I will give the material. I think I can stop at this stage. For any clarifications or questions, welcome.
I have one clarification.
Please, madam.
Is there any spectral study with respect to trace graphs? Spectra of trace graphs.
Active study? Oh, that's very complicated. You
That
see,
is spectra of trace graphs rather than spectra symmetric board.
Yeah, that's complicated, madam. Even in the case of zero divisor graph, the spectral study is gaining momentum. But for matrices, the structure is not very much known. The spectral properties really a worthwhile problem, I feel.
Other thing you talk about, you took N1 and N2 and talk about one is the subset of the other trace graph. I want to know in the subgraph. My question is a subgraph or induced subgraph?
It is isomorphic to a subgraph. I have put it a very careful word.
Okay, isomorphic subgraph.
It is isomorphic to a subgraph. Okay, because I need to induct some more elements in the bigger matrix. You know, one is a matrix of order N1, other one is a matrix of order N2. I need to induct some more elements, and that is why I put it subgraph isomorphic.
Okay, thank you. Thank you, very nice talk.
Thank you, ma'am. Thank you.
Knowledge, because I heard first time trace graph of matrices. I will see that one. Thank you very much. Thank you.
Thank you. Thank
you. Any other question or comments or information you need? Then please write to Professor Tamish Chelvam. Dr. Chelvam has given excellent talk. It creates curiosity. It has just analogy with the reconstruction of graph. But here reconstruction of graph means he has told trace of graph from the matrices. So it was an excellent talk, and on behalf of the academic committee, I am very much thankful to you, sir. And naturally, when it is well defined that the algebraic structures give rise to some graph, some matrices. But from matrices, can we trace the graph? Naturally, it was very interesting, and thank you very much, sir. Now
I thank the organizers for the opportunity, and I thank especially Professor Vaidya and Dr. Jirak Parasara.
Thank you, sir.
Thank you.
Thank you, sir.
In this session, I am very much happy to introduce. I am very much happy to introduce Father Joseph Varghese, who is a professor of mathematics, Crash, deemed to be University Bengaluru. Father is a spiritual leader, but also a leading researcher in the field of graph theory. He did his MSc from Madras University, while MPhil from Vinayaka Mission University, and PhD from Manamanyam Sundarnar University. But surprisingly, he is also having the degree in arts in economics. He has supervised 5 students for PhD, while 6 students for MPhil. I invite Father Joseph to deliver his talk, Binary Labeling in Graphs and its Variation. Welcome, Father Joseph.
Thank you. Thank you very much, Professor Vaidya, my mentor, my promoter in many ways and dear advisor. Dear organizers, especially Dr. Chirag and all the respected listeners. I would be speaking about some of the information where graph is delivering us. It can model several binary systems in the world. I've listed some of them. Every day we come across this kind of binaries. Day, night, to in, out, yes, no, adjacency, non-adjacency, gender, in case everybody's okay with that. Like, dislikes, there is no a single area where we cannot. So all these cases, graph can come to play a vital role in modeling. And this is actually hidden in many of the graph theory concepts also. Although graph gives this modeling, but the idea of domination, idea of independence, idea of especially split graph connect associated with the split graphs, covering and non-covering, degree, odd and even. Many of these cases, indirectly also we can see this kind of binary structure of the graph. Apart from graph being a binary concept where the adjacencies are concerned, other parameters associated with them are also concepts that are also in a hidden manner gives us binary feeling. What is this binary concept as such? You have to partition the vertex set or edge set or depending on our requirements, elements of graph into two parts by partitioning of the sets. It is possible in many ways. For example, domination, the example what I've given here, or the famous example of bipartite graphs, the split graphs, and the most celebrated, one of the celebrated theorems, Hall's marriage theorem. And you have in OR, we have assignment problem where jobs are there or the counters are there, persons are there, jobs are there, employees are there. These are all available, but I would be discussing with you three of those particular models: like, dislikes, on, off, ruling and opposition. This was actually a work done by social psychologists for several years, but then legendary Harari came with this classical work on the notion of balance of a signed graph in 1950s. He has introduced taking the idea of likes and dislikes in a community, in a group of people, modeling it as a graph called signed graphs, where the relations between members of a community could be represented as plus or minus depending on they are interested in each other or not interested in each other. So we call that particular model as a signed graph. And of course, with every signed graph, we can find underlined unsigned graph. We work on that as well. There is, how do we go with this life? One is directly looking at society, we can come with this likes and, but can we model as a general graph? If there is a possibility, we have to identify what way we need to give this edges labels, plus or minus. But along with that, although Harari did not give labels for the vertices because he is directly using social psychology concepts, later many people have introduced different types of labeling for vertices as well as. So it's a total labeling that is available for vertices as well as edges. One of the famous labelings is, which many of our colleagues also have worked on, is canonical marking. Canonical marking is given in such a, given a signed graph with the edges are signed, each vertex is getting labels based on the edges, incident edges. You take the product of the signs, you would get plus or minus, that would be the canonical marking of the vertices. One example is given over here. There can be all edges negative and all edges, but naturally it is all edges positive only. But there can be other distributions also. We have introduced in 2021, of course, the work was for 3 years, and finally it was published in 2021, Professor Mukti Ajari and myself, parity sign graph. This is a slight diversion from the general concept signed graph, but inherently every aspect of signed graph also we can get. First is we label all the vertices from 1 to n, if n vertices are there, the bijective labeling is given. Then based on the parity of the incident, the vertices incident to an edge, we give the labels plus or minus. You can see the reference here. So we have two distinct parity labelings given for the cycle C4. See, the labels are 1, 2, 3, 4. Both the ways labels are 1, 2, 3, 4. So depending on the parity, if both are odd or both are even, we give plus. Opposite parity means we give a minus. One of the major questions that is asked about the sign graph is from the time of Harari himself is the signed graph balanced? How do you call a signed graph balance? It is by any subgraph also can have a sign. Same as a graph has a sign, edge has a sign, vertex has a sign. Any subgraph also has a sign. What is the sign of that particular subgraph? You multiply all the edges of that particular subgraph. You would get a sign, that is a sign. So in case we have a path, we can multiply all the edges in that, plus and minus. Finally, what you get out as outcome is the sign of that path. So in case we have cycles available in a graph, we multiply all the signs, and if every cycle is positive, it is known as a balanced graph, signed graph itself. So is the sign graph balanced? That is a very important question. Depending on constructions of signed graphs, it is interesting to answer this question. Is the sign graph that is we have produced balanced one? Can we have a desired structure of a particular signing? Of course, as we have mentioned, this canonical marking or parity sign graph or several other labelings are possible. And is there a way in which we have a structure? Can we come with a rule? Or with a particular rule, what are the different structures that are being generated? What are the internal structures of the signed graph? Such as positive component. All the edges in that particular signed graph subgraph is going to be positive, or negative component. Formal definition I'm not giving, but general idea is that. So what are the substructures that are having a desired requirement? This is another very interesting problem. In all different types of labeling, what we give, can you count the number of sign graphs that are generated? Can you count the number of subgraphs depending on our requirement, given a conditions, enumeration problems? The largest size of a balanced edge set in a signed graph. It's an NP-hard problem, famous NP-hard problem. The smallest number of edges that must be deleted, frustration index, to make the signed graph balance. That also is an NP-hard problem. Yet another binary labeling is given by Harari himself indirectly, which was originally part of the social psychologist labeling. That is, they have actually started with a matrix. So you have n people in a society. If two people, instead of plus and minus, which Harari had given, until that time there was a particular construction by psychologists. If two people are liking each other, give the value 1. Not liking each other, give the value 0. There are two variations. So it's a square matrix, and the diagonal entries can be given either 0, or depending on a person likes himself or herself, then we can give 0 or 1. So this was observed. Later, several people have come with a new idea known as you give -1 for dislike, 1 for like, and 0 for indifference. But Harari reduced that to just plus and minus. But in connection with graceful labeling, the bit evaluation, several people have tried this 0-1 labeling. That is, given a graph, can we assign zeros and ones to edges or vertices depending on the case? One of the famous works is by Kahith. Kahith has come with a particular 0-1 labeling, which has got an application such a way that 0-1 labeling for the vertices based on functioning or non-functioning, liking or dislike. So Kahith has introduced this idea called cordial labeling as far as 0-1 labelings are concerned. What is this cordial labeling? It's very simple. Its cordiality is, you say there is no huge difference between the the vertex sets with the particular labels. So in case of 0, 1, only two parts are there. Either they are same or the difference of the number of vertices in each of the set is maximum 1. We can easily conceive the idea when is it going to be a difference. When the number of vertices or edges is odd, then the possibility of difference comes. If it is an even number, they are going to be having the same label. So now the question is, based on this rule, whether graphs are cordial or not. What is the rule that is to be done? Initially, we need to give the vertices label 0, 1, such that if each edge UV assigned a label coming from the gracefulness concept, f of u minus f of v. The vertices as well as edges labeled with 1 and 0 differ at most by 1. So this is, if such a situation exists, then the graph is known as a cordial graph. We have some expectations, symbol expectations and numeric computation. When we look at, we go with vertices labeled with 0 as v0, labeled with 1 as v1, and then the cardinality of that is taken as v0 and v1, and the difference has to be less than or at the most 1. And similarly, edges also. Our expectation is, our computation is based on this. Some obvious results, very simple results. All symbol connected graph with 1, 2, or 3 vertices are cordial. This was initially done by Kahit in 1987 itself. Non-triviality. Graphs with vertices 4 or more are to be explored. So many classes of cordial graphs which are not cordial or cordial are yet to be classified, characterized. So that gives you ample of opportunities for the researchers, especially without much serious background, much deep background in graph theory or mathematics, can explore. Even at school level, people can explore this. Some examples are given where the cordiality is available. This is a non-cordial graph. You can verify this. And there are several cycles which are non-cordial with respect to Kahit's definition. None of these would get this cordiality because initial labeling is for the vertex. So some famous results. Trees are cordial. N cycle with N is not congruent 2 mod 4 are cordial. Among the complete graphs, there are only 2, K2 and K3. They are trivially into other classes also. So generally a non-trivial complete graph from 4 onwards. Wheel on N plus 1 vertices where N is not congruent 3 mod 4 is generalized Peterson graph P and K, where N is not congruent to mod 4 is Cartesian product of 2 cordial graph of even size, complete bipartite graph. So generally, the work is still, although it was 1987 work, almost 35 years are over, but so much of problems are available where we can explore. We have a method, labels from 1 to n, chain the even numbers to 0 and odd numbers to 1. Cordiality condition is to be checked. Vertex cordiality is immediate because number of odd integers as well as number of even integers, the difference is at most 1. But the condition for the edges would make things complicated. For every 0, 1 edge, there should be a 0, 0 edge or a 1, 1 edge. That's a real problem here. Every 0, 1 edge, that means vertex is 0 on one side, sorry, edge is 0 on one side, 1 is on the other side. There should be a 0, 0. So that is actually the quantification that is required. One can begin with the tree of n vertices of our choice, insert edges as per our requirement. Once when you reach that, you put this into initially itself, vertices do not give the edges first. Labels you partition. As I've hinted you earlier, all the odd numbers you take one side, even numbers taken side, then check whether the graph can be generated, our original graph can be generated from these connections. So suppose that we have taken the edge partition as A, all the edges within this first set, B, all the edges within the second set. Let's call this as 1 and this as 2, this as 1 and this as 0, B 0 and A 1. Then all the edges among them, that is C. So how do we go with? We need to see A plus B is equal to C, or A plus B is less than C, or A plus B is greater than C. The cases as and when it emanates, we have to look into. A and B are of equal quantity is easy, very fine. But checking the intermediate edges is going to be complicated. As graph is said to be cordial if and only if vertex set can be partitioned into 2, such the difference of the number of edges between the partitions and the number of edges within the 2 partitions is at most another way of presenting it. So this is the way in which we start optimizing it. You have A set, B set, then all the C set, and you see that A plus B becomes C or little more than or little less than. Some of the research problems associated with this, we can look at characterizing families of cordial graphs. Issues with non-cordiality. What are the specific issues with the non-cordiality? We can even think about different indexes based on that. Same as in the case of balanced nature of signed graph, frustration index introduced. Depending on the type of non-cordiality of the graph, we can think about introducing different indexes. Practical applications in product graphs as well as hereditary properties. We can customize cordial labeling. There are many different variations of this cordial labeling that has happened. One is the 2004 work by Sundaram Pandraja and Somasundaram, that is product cordial labeling of a graph. It's just a rule. Please note down the concept. I would not be probably because I've started later, I may not be explaining all this. A total product cordial labeling. Its tautology is for edges and vertices together. It is not just edges difference is 1, vertices difference is 1, and totally when we take also number of vertices, edges and vertices together also, that cordiality has to happen. That is total product cordial. Difference cordial labeling is another interesting area. Came in 2013. Divisor cordial labeling came in 2011. K cordial labeling of a graph. And Professor Mukti Acharya has introduced the C cordial, canonical cordial labeling. C stands for canonical. Professor Mukti Acharya has a vast collection of studies on signed, especially these cordiality conditions for signed graphs. This is a mix of now cordiality as well as the signed graphs. Both are binary labelings. Implications of that. Balanced cordial labeling in signed graphs came in 2016. There is another binary labeling that is coming from the idea of K stratification. A particular K stratification is the stratifying of the vertex set with the K different colors. It need not be the vertex, the color classes need not be independent. So instead of K colors, if we just take 2 colors, it is known as 2 stratification. So we can apply a rule. It does not matter which rule we need to have. So we decide a rule. You just give 2 colors. Specifically, Chatan and team, when they introduced, they went with the red-blue stratification. Because as I was mentioning in the beginning, there was a particular reason why they went for the red and blue. I would explain that a little later. The color classes need not be independent. That does not make the thing easy. It is going to be complicated only depending on our way in which what we want from the graphs. At least 1 red vertex should be there and at least 1 blue vertex should be there. The work came in 2003. and not much work is done thereafter on this true stratification. I'm going to give you some open problems or hints to open problems. So this is one example for that. Two stratified graph. So adjacency and other conditions, class difference and other things are not here. But clearly by partitioning the vertex into such a way that some of the vertices get red color and some of them get blue color. Now comes interesting work. Why this was introduced? Because they are researchers from America. They have this two-party system, blue and red party, or Republican and Democrats and Republicans. So with that in mind, people have different opinions. They can be classified into either use proper any of those parties, ruling and opposition, or rulers and opposition. Now, this two stratification induces again two coloring for the graphs. That's very interesting and exciting work, which only very few papers, only 3 or 4 papers have been done, work by people, but so much of work we have started working on, but then paper is sent for publication, especially two stratification with the help of triangles. Now this is one example where two stratification is initially given that gives labels for the other graphs. We start with these smaller graphs. Let's take K2 or P2 and P3. These are all two stratified graphs. Red and blue, it's our choice. These are the possibilities. So the first graph has only one possibility because minimum one color has to be red, minimum one color has to be blue. And second graph, the P3 has only these possibilities, 3 possibilities at all. Now, this is a rule that is going to be given such a way that two stratification of a graph can induce a stratification for the graph of our choice. Let us call a two stratified graph as an F graph. Designate a blue vertex as a root vertex. One of the vertices as a root vertex. For example, here, this can be a root vertex. Here there is only one, but there are 2. So here we can take this vertex on the top as root vertex. Here it's symmetric. There is no possibility, it's the same. So here there is a lot of difference in 3, in the second graph, the middle graph here. Now comes the interesting coloring pattern. Let G be an arbitrary graph. Assign vertices red or blue for a new graph such that every blue vertex, if there is a blue vertex available, then it should belong to an F in G. Hope you are getting it's very complicated work in many sense because of the impact of this. That is why many people are not working on it, I suppose. Assign vertices red or blue for an arbitrary graph. So therefore, if a graph is coming with all red, there is no problem. If a graph is having at least one blue vertex only, the problem is going to begin. So all red is possible. Don't have to worry about it. The new graph. Already the two stratified graph has got 2 colors. Now given an arbitrary graph, if all the vertices are given red, coloring won't come. It is justifying the rule here. It's trivially true. But in case at least one of the vertices is having blue color, then keeping that particular vertex as a root vertex, it should be part of an F. What is it? F is our choice. I show you some examples now. Let us take the first graph as an F graph. This K2 with the 2 colors. Look at this second graph. Is it an F coloring? If this is F, this first one is F. Yes, because there is only one blue vertex and it is part of a K2 which is having both ends different colors. This red has no issue at all because it is not, it has nothing to do, it is not blue. That is a simple, the trivial case. Now look at the second graph. This middle vertex is adjacent to a red vertex. Therefore, this is an F. But what about this vertex in the bottom? It is not part of a P2 with one end red and one. So this is not an F coloring. The middle one is not an F coloring. Whereas this one, this is interesting. See, there is only one red, but this red blue on the top would satisfy the condition for an F coloring. This also would satisfy a condition for F coloring. I give another example. This is our F graph. This is okay. This is okay. And this is not okay. Now, I take a larger graph. P3 with one of the vertices is red and two others are reds. One of the vertices is blue and the other two are red. Now we have one blue. Check in the first case. It is not part of an F. Therefore, the first one is not an F coloring based on this F graph. But the same F graph, this gives us the F coloring. Look at this. One blue, then there are two red edges. Then there is one blue, there are two. Either these two or these two we can take. Therefore, it is. Whereas this graph, one blue, two red, one blue, two red, one blue, two red, this is also fine. What are the applications of that? See, this particular graph with the red and blue, in fact, that is domination only. If you minimize the number of blue vertices, it is same as our domination only. A P2 with one red and one blue, you insert that in a larger graph with the red blue. You insist that every blue should have red there. So this is going to give us different types of domination starting from K2, and depending on each F, it gives different types of dominations. Some basic works are given in the work by Chattand and the team, but not much work is done after that. Independence can be explored with the help of this. Coloring can be explored with the help of this. Perfect graphs based on this particular coloring can be explored. Now, there is a new concept by Chattand, Kono and Shang introduced last year. Only 3 papers are out so far. This is actually what they give as a red-white coloring, because I was speaking about red-blue coloring. I continue with the red-blue coloring. Actually, originally in the paper, it is red-white coloring. So given a red-blue coloring with at least one red vertex, each vertex V is assigned a D vector. You might be remembering metric dimension. Kind of that is going to be worked out here. Metric dimension. So each vertex V is assigned a D vector. A vector is, or it is also known as D chord. A chord is, how the chord is generated? Interestingly, this is the way. If the ith element of D is the number of red color vertices at distance I from V. In the vector, we have position 1, position 2, position 3, it goes. So the first element in that vector is the number of red color vertices at distance I from V, that particular vertex. Make all the D vectors distinct. Is it possible or not? Not all graphs have this possibility. This particular coloring is available, then that particular graph has got identification coloring, or in abbreviation, they have used the term ID coloring. The least number of red vertices needed for an ID coloring is the ID number of a graph. As I have hinted, only 3 papers are out. Good amount of research is going to come in these years, but we can also step into this if you are not into serious other areas of work. even as part-time, as a entertainment work, you can do it. These are some examples. They have proved that caterpillars of maximum degree 3 with minimum of 4 vertices, the ID coloring number is 3. These are 2 examples. They are caterpillars as well as they are double stars. These are the ID colorings as well as the coloring number. This is achieved by the minimum colors, 3 colors. So what are the possible areas of these binary labelings? We can explore graphs induced by one type of labels, either 0, 1, plus, minus, or red, blue. We can mix them also. Combining these labels, as I had, as Professor Muktiacharya has done, we can cordiality from, we can think about signed graphs, then we can think about coloring also associated with this. You can combine any of these. Enumeration is a very interesting work that can be done in each of these cases. How many different substructures are available, how many different labelings are available, as well as how many different substructures are available, and any type of label. Cordiality. In each of these cases, cordiality can be explored. Generating rules. That is one robust area anybody can work on. Can you give a generating function, a rule that would induce particular labeling? We can connect with other graph parameters also. Thank you very much.
Any question, comments? Then please unmute yourself and connect with us. So, Father Joseph has delivered an excellent talk, because generally the binary labeling in general and cordial labeling in particular, the name of the paper by Kahit itself is a weaker version of the graceful and harmonious labeling. But Father has represented the binary labeling as a very rigorous labeling, as it has many potential applications. So thank you, Father, for making your talk very interesting by considering it from a stratification problem and represented the binary labeling in a very magnificent way. So it shows your expertise in the field of labeling. Thank you very much, Father. And I'm also very much thankful to the organizing committee to invite me and to give an opportunity to chair this session. Thank you very much.
Thank you, Sameer sir, for chairing this wonderful session. And now we will take a short lunch break for 45 minutes. And since the session commences at 2:15 p.m., I request all the participants to join the respective link by 2:10 p.m. And then
Thank you all.
Yeah.
Thank you, Father, for being with us.
Thank you. Thank you.
Thank you, everybody.
Thank you, sir.
Thank you,
The
Chirag.
next session starts at 2:15.
Yeah.
2:15. Right. Okay, sir.
Thank you.
Thank you, sir.
Hello. Welcome back, everyone. Hope everyone had a great lunch. And now we'll start the next technical session, which will be chaired by Professor Ambat Vijay Kumar, sir. Sir is an emeritus professor, Cochin University of Science and Technology, Kerala. He's a fellow member of Institute of Combinatorics and Applications in Canada and a winner of Broad Outlook Learners Teacher Award in 2007. He's a director in the Center for Interdisciplinary Studies, CUSAT, and honorary deputy director at the Center for Science and Society. He has produced 12 PhDs and has 70 publications. He has delivered many talks in the national and international conferences, including Hungary, Italy, China, Canada, Taiwan, Czech Republic, Germany, etc. And he's the vice president of the Ramanujan Math Society and has written more than 60 popular articles in various aspects of mathematics in Malayalam and in English for the students. So it's an honor to have you here, sir. So I'll hand over the session to you, sir.
Chirag, I don't know, my video is not working, but am I audible?
Yes, sir, you're audible.
Sir, you're audible. It shows that your bandwidth is low.
Pardon?
Sir, the internet speed is low. That's what the message I am getting.
Oh, it's okay now. But anyway, I'm audible, isn't it?
Yes.
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 Okay, good afternoon all. I have great pleasure to introduce Professor Ramane, my good old friend, who is currently chairman of the Karnataka University, Dharwad Department of Mathematics. He is a PhD from Karnataka University in 2002. And current areas of interest include spectral graph theory, chemical graph theory, graph energy, and so on. He has produced 13 students for a PhD. And now he is going to give a talk on some characterization of complementary equi-energetic graphs. Over to Raman.
Good afternoon to all of you. Let me first of all thank Chirag Barsara for inviting me to give a talk in this national conference, and also I am thankful to the Vijay Kumar sir for his inspiration for me to do all such work. Thank you, sir. Thank you for your kind words. I am audible now?
Yes, sir. Yes, sir. You are audible.
I will share now my screen. Is it visible?
Yes, sir. Yes, sir.
Okay.
Kindly, sir, make it full screen.
Yeah. Okay. So my topic is some characterization of complementary equi-energetic graphs. Okay, there are a lot of work done on the energy of a graph. So energy of a graph is sum of the absolute values of the eigenvalues of its adjacency matrix. Okay, this is a basic definition, but there are several variants of graph energy based on the different matrices. We are dealing here only with the adjacency matrix, and the graphs, two graphs are said to be equi-energetic if they have the same energy. Okay, of course, the isospectral or co-spectral graphs are the same energy, but we need to deal with the non-co-spectral graphs. Okay, the main topic of this talk is to find the graphs which are equi-energetic with its complement. Okay, so such graphs we call it as a complementary equi-energetic graphs. So as I told, the energy of a graph is defined as the sum of the absolute values of the eigenvalues of the adjacency matrix of a graph. And this concept was introduced by Ivan Gutman from Serbia in the year 1978. And it is intensely studied since it can be used to approximate the total pi electron energy of molecules in chemistry. Okay. So two graphs are said to be equi-energetic if they have the same energy. So of course, isospectral or co-spectral graphs have the same energy because they are having same eigenvalues. Okay, but the graphs which do not have same eigenvalue, even though their energy is same. So such graphs are more interested here. So we'll consider a finite graph G, which is simple undirected, having the n number of points and m number of lines or edges. The vertex set will be denoted by V of G, with the vertices labeled as V1, V2, Vn. Edge set is denoted with E of J, and the edges are labeled with E1, E2, Em. Okay. So adjacency matrix of a graph G is a square matrix Aij of order n, in which the entry ijth entry Aij is 1 if the vertex Vi is adjacent to vertex Vj, otherwise it is 0. Okay, so if there is a line between 2 points, then we'll put 1, otherwise 0. So diagonal entries are 0 here. And the characteristic polynomial of graph G is nothing but the characteristic polynomial of its adjacency matrix, denoted by phi of G lambda. That is determinant of lambda I minus A of G. I is a identity matrix of order n. Okay. So eigenvalues of Ag denoted by lambda 1, lambda 2, lambda n, they are called the eigenvalues of Ag, and their collection is called the spectrum of G. Okay. So two non-isomorphic graphs are said to be co-spectral if they have same spectra. That is, they have the same eigenvalue, then these two graphs are called co-spectral or sometimes isospectral. So suppose if lambda 1, lambda 2, lambda k are distinct eigenvalues with respective multiplicities m1, m2, mk, then the spectrum of G can be written in this fashion, that is in the bracket lambda 1. It means that lambda 1 appears m1 times, lambda 2 appears m2 times, and so on, lambda k appears mk times. Okay. So m1 plus m2 plus mk is n, total number of points or total number of vertices in a graph. So energy of a graph G is summation of mod of lambda I ranging from 1 to n, and it is denoted by this notation epsilon G. Okay, or we call it as E of G. So for example, consider this graph with 6 points. Okay, of course it's a regular graph of regularity 3. Its adjacency matrix is given here. Okay, so characteristic polynomial of this graph is the lambda raised to 6 minus 9 lambda raised to 4 minus 4 lambda cube plus 12 lambda square. And its eigenvalues are 3, 1, 0 2 times and minus 2 2 times. Okay, so energy of this graph is sum of the absolute values of all these eigenvalues, that comes to the 8. Okay, so energy of this graph is 8. So little bit about the how it is related with the molecular orbital. Okay, so consider this butadiene. Its molecular graph is here. That is, carbon bonds or carbon atoms are taken as a vertices. Okay, and if there is a carbon bond, means bond between the two carbon atoms, then we'll put the line. Hydrogen atoms are ignored. Okay, so this is a molecular graph of this molecule. Then its matrix H defined as, if there is a line between 2 points, then we'll put beta, otherwise 0, and diagonally alpha. Okay, diagonally alpha. So it is turned to the alpha I plus beta A. A is the adjacency matrix of this graph. Okay. So in the ground state level, when alpha is 0 and beta is 1, this H becomes a simply adjacency matrix. Okay. So since H is alpha I plus beta A, the eigenvalues of I are all ones, and the eigenvalues of A are suppose lambda 1, lambda 2, and so on, lambda n. Then the eigenvalues of this matrix H will be denoted by epsilon I as alpha plus beta lambda I. Okay. So in the HM appliance, the total pi electron energy is summation of all these. Okay, Gi into epsilon I, where Gi is the occupation number. So if we put this epsilon I as alpha plus beta lambda here, it turns to the total pi electrons of that molecule is n alpha plus beta into summation of Gi into lambda I. Okay. So in most of the cases, this Gi is 2. Okay. That is when lambda is positive, then Gi is 2. Okay. And lambda is negative, then Gi is 0. Okay. So for majority of conjugate, Gi is 2 if lambda is positive, and it's 0 if lambda is less than 0. Therefore, this E pi, that is this energy, E pi, total pi, can be written as n alpha plus 2 times summation of lambda I. Okay. Where summation goes over all positive eigenvalues. Okay. So 2 times beta times summation of lambda I, summation goes over only positive eigen, because for negative eigen, this Gi is 0. Okay. So naturally it will vanish there. And if lambda is 0, then that term also goes vanish. Now, the trace of a matrix, adjacency matrix is 0. So sum of the positive eigen is same as the sum of the negative eigenvalues. Okay. They differ only in the sign. So instead of writing 2 times summation of lambda I over the positive eigen, it can be written as summation of mod lambda I, where I ranges from or all eigenvalues 1 to n. Okay. Now here alpha is fixed, n is fixed, beta is fixed. So what is left? Only this is a variable, summation of mod lambda I. So that quantity is called the summation of mod lambda I is 1 to n, is called energy of a graph. Okay, so thus energy of a graph is defined as summation of absolute values of the eigenvalues of a graph. Okay. Then two graphs are said to be equivalent. Already I told if the energy of G1 is energy of G2. So, okay, so this concept introduced first time in the year 2004 in simultaneously in these three papers. Okay, the Balakrishnan, then Branko-Stanley Goodman and our group. Okay, in the same year 2004, we consider this concept of equinegeticity. These two graphs are said to be equinegetic if they are having the same energy. So for obvious reason, co-spectral graphs are equinegetic. The simplest non-trivial example of equinegetic graph is from here. So if we take this K3, then C4 and two K2s. Okay, so eigenvalues of this K3 or C3 are 2 minus 1 minus 1. Eigenvalues of cycle C4 are 2 0 0 minus 2, and the eigenvalues of two K2s is 1 1 minus 1 minus 1. And their sum, that is absolute sum, or sum of the absolute values of these eigenvalues is 4. So these are equinegetic graphs. Now see here, first graph has 3 points, whereas second has 4 points. Here, both the GB and these two K2 have the same number of points, but one is connected, one is direction. So if you go and impose the additional conditions, that is both graphs should have same number of points, both should be connected like that, then the problem of then finding of such graphs is not that easy. So the smallest pair of non-co-spectral connected equinegetic graphs with same number of points, okay, is this cycle C5 and this tetragonal pyramid will denote it by GD. Okay, so both are having same number of points. The eigenvalues of these are 2 root 5 plus or minus 1 by 2 and minus root 5 plus or minus 1 by 2. Okay, for the cycle C5, and for the second graph, the eigenvalues of root 5 plus 1 0 0 minus 2 minus 2. And if you take the energy of these two graphs, it is turned into the 2 plus 2 root 5. Okay, so these two are not a co-spectral, okay, but energy is remaining same. And both are having same number of points. Okay. Whereas these two graphs, G1 and G2, where the number of points is also same and the number of lines also same. Okay, they are having 9 points. Okay, and each is regular of degree 4. Okay, so both are having same number of points, same number of lines, and there's a characteristic polynomial is given here. Okay, so looking to the characteristic polynomial, we can see that they are not a co-spectral. Okay, the eigenvalues are different, but if you take the energy, it is turning to the 16. Okay, so these two graphs are having same number of points, same number of lines, they are connected. Okay, and they are equinegetic. So there are several results obtained in the literature on the equinegetic graphs. For example, Balakrishnan in considered equinegetic graphs for using tensor product for all n congruent 0 mod 4. Branko-Stanley, they listed some equinegetic trees. Then ourselves obtained the energy of second line graph of regular graphs, and thus infinitely constructed the many equinegetic graphs. Again, Stephanie gave the construction of equinegetic graph for all n congruent 0 mod 5. So this is a development on this subject. Then in 2005, we did energy of the complement of identity line graphs, and we found there also equinegetic graphs. Then we constructed the equinegetic graphs by join of two graphs for all n. Okay, so we shown that for a given n, there exist two graphs which are not co-spectral but having the same energy. So on how construct equinegetic bipolar graphs. Indula and Vijay Kumar, they gave the equinegetic self-complementary graphs. Okay, so graphs are self-complementary. If you take G1 and G2, they are not self-complementary each other. Okay, but G1 is a self-complementary, G2 is self-complementary. Okay, such graphs also having the same energy. So now the topic is here, the graph which is equinegetic with its complement. That is, if G is a graph, then energy of G equal to energy of G bar. Okay, okay. So this is the main topic of this talk. Okay, so naturally self-complementary graph satisfy this. Okay, okay. So we need to find the graph should be non-self-complementary, and energy of G is equal to energy of its complement. So this is a simple example here, C4 and its complement, that is 2 K2s. Okay, so eigenvalues of C4 are 2 0 0 minus 2, whereas the eigenvalues of its complement are 1 1 minus 1 minus 1, and energy is 4. Okay, so here C4 is connected, whereas C4 bar is not connected. But there is a graph whose complement is also connected. Okay, so considering C6 and its complement C6 bar. Okay, so this is the smallest non-self-complete graph satisfying energy of G equal to energy of G bar, where both G and G bar are connected. So eigenvalues of C6 are here listed 2, 1, 1, minus 1, minus 2, and its complement 3, 1, 0, 0, minus 2, minus 2. And from here, we can see the energy is same. Okay, so this is a pair of a graph which is both both the graph and its complement are connected and having the same energy G and G bar. Okay, we'll use this result for the further results. So the SAC given in 1960, that is, suppose G is a regular graph of order n with eigenvalues r lambda to lambda n, then the eigenvalues of complement graph G bar are n minus r minus 1 and remaining minus lambda 2 minus 1, minus lambda 3 minus 1, so on, minus lambda n minus 1. Okay, so I list here some graphs and then some characterization. Okay, so for n greater than 2, if you consider G as n copies of Kn, okay, then the energy of G equal to energy of G bar. Okay, so proof is simple from the spectra of this graph. Okay, so we know that the eigenvalues of a complete graph are n minus 1 and the remaining minus 1. Okay, so eigenvalues of n Kn are n minus 1 n times and minus 1 appears n into n minus 1 times. So from here, the energy of G is 2n into n minus 1. And then using the Jack's theorem for the eigenvalues of a complement of a regular graph, we can get the eigenvalues of G bar. Okay, because we know the eigenvalues of G. Okay, so from that, you can get eigenvalue of G bar as n square minus n 1 times minus n minus 1 times and remaining 0. And from this, the energy of G bar is 2n into n minus 1. So energy of G equal to energy of G bar. Okay. So in 2002, in my thesis, I reported the energy of line graph of complete graph KPP is same as its complement. Okay, for P greater than equal to 2. Okay, but that time the word complementary equality graph was not done. Now the people are calling the such graphs are complementary equivalent. Okay, there we have shown only one result. Okay, where energy of the line graph of KPP is same as its complement for P greater than 2. And here the line graph of K33 is self-complementary. Others are not self-complementary. Others are non-self-complementary. So here recently we are done for any complete bipartite graph. Okay, and here it is a complete bipartite which is a regularity P. Okay, but here we are shown for any complete bipartite graph. Okay, so PQ greater than equal to the energy of line graph of KPQ is same as its complement. So spectrum of LKPP is this. Okay, so from here we can get the energy as 4 into PQ minus P minus Q plus 1. Okay, the line graph of KPQ is a regular graph. Okay, line graph of KPQ is a regular graph, so we can get the eigenvalues of its complement. So eigenvalues of complement are listed here. Okay, because KPQ is has PQ vertex and is a regular of degree P plus Q minus 2. And from here, the energy of this graph, that is complement of L of KPQ, is again same as 4 into PQ minus P minus Q plus. Okay, so this is by simple calculation from taking the spectra of both the LKPQ and its complement. We can see the LKPQ is a complementary equivalent graph for all PQ greater than equal to. We know that Cartesian product of two graphs is a graph denoted by G1 cross G2 with its vertex set as Cartesian product of VG1 and VG2, and which two vertices U1, U2, V1, V2 are adjacent if either U1 is adjacent to V1 in G1 and U2 is V2, or U1 equal to V1 and U2 is adjacent to V2. Okay, so this is a Cartesian product. Similarly, the tensor product of two graphs denoted by G1 cross G2 with vertex set VG1 cross V of G2. Okay, and two vertices U1, U2 and V1, V2 are adjacent if and only if U1 is adjacent to V1 in G1 and U2 is adjacent to V2 in G2. Okay. And if we know the eigenvalues of G1 and G2, we can write the eigenvalues of their Cartesian product as well as the tensor products. Okay. So if lambda 1, lambda 2, lambda n are the eigenvalues of G1 and mu1, mu2, mu are the eigenvalues of another graph G2, then the eigenvalues of the Cartesian product G1 cross G2 are simply lambda I plus mu j. I is 1 to n, j is 1 to m. Similarly, the eigenvalues of tensor product G1 and G2 are lambda I into mu j. Okay, one is I is 1 to n and j is 1 to m. So we'll use this result for the further development. So in 2008, Beneficio, Vinagre and Ebru proved that energy of the Cartesian product of Kp and Kq is same as the energy of the tensor product of Kp and Kq. Okay. But recently we observed that this Kp cross Kp, Kq is nothing but line graph of Kpq, and this tensor product Kp and Kq, tensor product of Kp and Kq is a complement of line graph of Kpq. Okay, so naturally Kp cross Kq is a complementary equinegetic graph. Okay, because it is a line graph of Kpq and this is a complement of line graph of Kpq. Another one, suppose G is a complement of nkn, then for m less than equal to n, okay, m less than n, the energy of G cross km is same as the energy of its complement, that is complement of G cross km. Okay, so spectrum of complement of nkn is this. Okay, and the spectrum of km is m minus 1 and remaining minus 1. So using these results, okay, that is the eigenvalues of the Cartesian product as well as the tensor product, we can get the eigenvalues of G cross km as this, and from here the energy of G cross km is 2n into n minus 1 into 2m minus 1. Okay. Similarly, the G cross km is a regular graph, so we can get the eigenvalues of its complement. Okay, and eigenvalues of its complement are listed here. So from this, the energy of G cross km bar is again same, 2n into n minus 1, 2m minus 1. Okay, so both these, this G cross km is a complementary equinegetic graph, where m is less than equal to n. Okay, but suppose if m is more than n, so if G is nkn bar and m is more than n, then energy of G cross km is this, that is 4mn square minus 4n square minus 2mn plus 2n minus 2m plus 2, and the energy of its complement is this one. Okay, and if you compare this, the difference between these two energies, that is energy of G cross km bar and the energy of G cross km is 2 times n minus 1. Okay, so for m more than n, they are not, this graph is not a complementary equinegetic. Okay, where n is more than 2. Okay, so, but here difference is just depending on the number of points of, depending only on the n. Okay, not on m. Okay, so you take the Cartesian product of G with any km. Okay, the energy is, their difference is turning to the 2 times n minus 1. So this is also one of the topic one can see that what is the difference between the G and G bar. Okay? If it is 0, then we call it as a complementary equinegetic. So strongly regular graph with energy of G is energy of G bar. So we know that strongly regular graph with parameters n, r, a, b is a regular graph of degree r with n points, and in which two adjacent vertices have exactly a common neighbors and any two non-adjacent vertices have exactly b common neighbors. Now if G is a self-complementary, then it's G is a strongly regular graph, then its complement is also strongly regular graph with parameters are listed here. n minus r minus 1, n minus 2 r plus b minus 2, and n minus 2 r plus. Okay, so if G is a self-complementary, strongly regular, its complement is also strongly regular. And the spectrum of strongly regular graph given in terms of parameters is like this. If G is a strongly regular graph with parameters n, r, a, b, then its eigenvalues, the spectrum of G is r appears 1 times. Then the eigenvalue half a minus b plus t appears these many times. That is half n minus 1 minus delta by t. And another eigenvalue half a minus b minus t appears this much. So where t is square root of a minus b square plus 4r minus b. And this delta is 2r plus n minus 1 into a minus b. Okay, so knowing to the spectrum of this, we can find the spectrum of its complement G bar because it is a strongly regular graph. Okay, so that is a regular graph. So using the Sachs theorem, we can get the the eigenvalues of G bar also. Okay. So here are some examples. The strongly regular which are satisfying the energy of G equal to energy of G bar. Okay. So if G is a strongly regular graph with these parameters, that is 4n squared, 2n squared minus n squared minus n squared minus n, then the energy of G is equal to energy of G bar. Okay. It is easy to see because spectrum of G can be obtained from the as we know, the spectrum of the strongly regular graph with the in terms of parameters and the spectrum of G bar. And from here, the energy of these two graphs is turning to 2n into 2n minus 1 into n plus 1. Okay, so you'll get here several examples. Okay. So if you put n is 2 in the above theorem, then we get a strongly regular graph with parameters 16, 6 to 2, which is a Srikande graph. Okay. So energy of a Srikande graph and of its complement is 30. So Srikande graph is also one of the example of complementary equinegative graphs. Okay, so Srikande graph has so many properties. This is another one property added here. It is a self-complementary equinegative. Another, if G is a strongly regular graph with parameters given like this, then energy of G equal to energy of G bar. Okay, so again, using the spectrum of both G and G bar, we can see the energy of G and energy of its complement is 6 into n minus 1, n minus 2. Now here is the characterization. Suppose G is a strongly regular graph with parameters n, r, lambda, mu. Okay, instead of AB, I have taken here lambda, mu. Okay, then energy of G equal to energy of G bar if and only if n minus 2r minus 1 is delta by t. Okay, where t is square root of lambda minus mu square plus 4 into r minus mu, and delta is 2r plus n minus 1 into lambda minus 1. Okay, the proof of this we are given using the spectrum of both G and G bar. Okay, and finding its energy and then equating, we get this. So spectrum of G is here. So energy of G will be in this form. Okay, r plus 1 by 4 into n minus 1 minus delta by t and so on. Okay, then spectrum of G bar is this. So from here, the energy of G bar will be in this expression number 2. Okay, so expression 1 gives the energy of G, where G is a strongly regular graph, and the expression 2 is energy of G bar. Then equating these two, we get n minus 2r minus 1 equal to delta by t. Okay, so if energy of G equal to energy of G bar, then this relation satisfies. The converse is obvious. Suppose conversely n minus 2r minus 1 is delta by t, then we need to show that energy of G is energy. So on the contrary, suppose energy is not same, this implies this is not equal. It's contrary. It means that energy of G equal to energy. So energy, if G is a strongly regular graph, then it is a self-complementary equinegative, that is energy of G equal to energy, if and only n minus 2r minus 1 is delta by t. So this is a characterization of the complementary equinegative graph, strongly regular graph. So recently, I saw these two papers. That is Jaunovic, it appeared in the journal Match in 2021. Okay, and recently, just 4 days back, I saw this paper, linear multilinear algebra, that is Podesta and Videla. In these two papers, the above result is given, same result, but they use the different technique to prove it. Okay, so with the difference between the eigenvalues, okay, and that technique they use to show that the same result for the strongly regular graph. Okay, the strongly regular graph, which is it should be a complementary equinegative and only if that condition satisfies. Okay, so in these two recent paper, one can see here. Okay, with even in this Podesta and Vidal paper, they are given the conditions with in terms of parameters. Okay, in terms of parameters of the strongly regular graph. So the strongly regular graph G with these parameters, when m is less than n plus 1, it satisfies the above condition. So energy of G equal to energy of G bar here. Okay, so with this parameter, it is always complementary equinegative graph. Okay. This another result. If G is a strongly regular graph of order n with regularity R is n minus 1 by 2. Okay. If energy of G is energy of G bar, then G and G bar are co-spectral. Okay, here reverse way. If energy of G is energy of G bar, then G is co-spectral with its G bar. Okay, provided the regularity is n minus 1 by 2. some more graph satisfying this relation, that is energy of G. Okay, for R regular graph, R more than 3, energy of L square G is energy of its complement if and only if G is a complete graph on 6 point. Okay, complete graph on 6 point. Then if you take C4 cross K2, then C4 cross K2 and its complement, they are having the same energy. If you take the strongly regular graph with parameters, this 5701, that is Murray graph. Okay, so Murray graph and taking its complement. Okay, complement of Murray graph with Cartesian product with K2 and its complement. Okay, so they are having same energy. If you take Sebezier graph CG, which is again strongly regular graph with these parameters 16502. Okay, if you take CG bar, its Cartesian product with K2 and then its complement, they are also having same energy. Okay, so taking strongly regular graph and making some graph products. Okay, and then getting such graphs means having a complementary equinegaticity. Okay, so here one need to find the characterization. Okay, with graph operations or graph product, we can say. Okay. Then recently, okay, just recently we obtained these results. For n more than 3, the cycle Cn is complementary equinegetic if and only n is 4, 5, and 6. Okay, so only for n is 4, 5, 6, the cycle Cn is complementary equinegetic. That is, energy of Cn is same as the energy of its complement. So C5 is here self-complementary. Okay. Similarly, the path Pn is complementary equinegetic if and only if n is 4. And for n is 4, the P4 is a self-complementary graph. Okay. Then the complete bibutyl graph KPP is complementary if and only P is 2. Okay, that is only for K2, that is C4 and its complement, that is 2 K2s. This is another one. If in one of the slide I have shown that L square of G is same as energy of L square G equal to energy of L square G bar if and only if G is K6. Okay. So here, if G is a regular graph of order n0 and degree r0, and let K is get the kth iterative line graph of G of degree Rk and of order Nk. Okay, so Nk is the number of points in LKG. Okay, and Rk is the its degree. Then energy of LKG is energy of its complement if and only if Rk is not equal to 40 or 40 plus 1. Ali, Elomai, Mansoor, and Aston, okay, they determine all graphs with at most 10 vertices satisfying this relation, energy of G equal to energy. Of course, they use the computer search, and using that, they are listed all the graphs satisfying up to 10 points. Okay, up to 10 points, satisfying energy of G equal to energy of G bar. Okay. So among all graphs of order at most point, there is only one pair which is complementary, that is C4. Okay, this C4. Of course, this CPI is also there, but CPI is a self-complementary. Okay, so here we need to trace on the graph should be non-self-complementary graph, and its energy is same as the energy of its complement. So among up to 6 points and 7 points, these are the pairs. Okay, having satisfying the complementary equinegaticity. Then all possible pairs of complementary graphs with 8 points. These are the pairs. Okay, so they are listed all these graphs up to 10 points. These are the graphs with 9 vertices. These are the graphs with 10 vertices. So list continues here. Remaining pairs with 10 points, satisfying energy of G equal to energy of G bar. Also, they have determined all the graphs up to 10 vertices satisfying the energy of line graph, energy of LG equal to energy of LG bar. Okay. So now problem is finding structural and spectral properties of graphs satisfying energy of G equal to energy of G bar. Okay. So one need to get other parameters or other properties of a graph which satisfy this relation. Okay. So for strongly regular graph, the characterization is done. But for other graphs or any other characterization, still it is need to dig. So these are some references. Okay, so these are the two recent papers, Jovanovic, Jojic, and this one, Podesta video. Okay, recently they appeared on this topic. And this is the paper, this one, third one, where we first time introduced that equinergetic means complementary equinergetic graphs here. Okay, now people are working here. Thank you.
Ramane, can you please take the first slide where you introduce that strongly regular graphs?
1 minute. Okay.
Some parameters were mentioned.
Yeah.
Next one.
Next one, huh?
Next one, yes. Next.
This.
Okay. Okay, you have a third parameter and fourth parameter equal.
Yeah.
That means the strongly regular graph is coming from a balanced incomplete block design.
Yeah, correct.
So that point also you can mention.
Yes.
And Srikhanda graph is an example.
Yeah. So Srikhanda graph is one of the example, correct.
So did you try other families of strongly regular graphs?
No, sir. We have done this, that, OA parameter something is there, sir. OA parameters. Okay. This is coming from, again, design only. Okay.
This notion of polygraph.
Polygraph.
Infinite family of strongly regular graphs. And I mentioned in my presentation about the Moore graphs. So you have tested for C5 Peterson graph, and Hoffman-Singleton graph. So do you mean to say that all the known 3 Moore graphs are satisfying your requirement?
That we need to check it, sir, then.
There are only 3 Moore graphs now.
Okay.
We have a parameters of the 4th Moore graph, possible parameters, but we don't know whether such a graph exists. Okay, that's what I mentioned in my presentation.
Correct.
So we can just check C5 Peterson graph, Hoffman-Singleton graph.
Okay.
These are the only 3 known Moore graphs.
Moore graphs, correct.
You can check whether that satisfies energy of G is equal to energy of G bar.
This condition, okay. Yeah.
And there is a long series of papers, long back, maybe at least 20 years back.
Okay.
On properties of graph common to G and G bar.
Okay.
Jin Akiyama.
Yeah.
Okay, there is a properties of graphs in which G and G bar have the same connectivity,
same properties.
Same chromatic number.
Okay.
They are both connected. So many properties they have studied.
Okay.
So your problem can be put in that framework.
That problem, correct.
Properties of graphs which satisfies energy of G is equal to energy of G bar.
G bar, yes. Correct. Thank you.
Fine. Are there any other questions?
So can we have the PPT of this?
Pardon?
Can we have the PPT of all your presentations, because it should be helpful when we were working out the problems?
Okay. I will share with this organizer. You can get it from them. Okay.
Sir, Ambat sir, can you also share it, sir? It should be helpful.
Yeah, let me check. Any other questions or comments?
Thank you, sir.
In fact, there are, because I am a fan of Srikante, Srikante graph properties are, as last time when I asked a question in the Trinidad conference, look at the gamma graph of Srikante graph. Very surprisingly, after 2 months, some group in Tamil Nadu, they are working on it and we are looking into the results.
Okay.
So Srikante graph, many other properties are there, which are still don't know. Okay, good. Any other comments or questions? Okay, if not, let us thank the speaker and over to Chirag.
Thank you, sir.
Thank you.
Hello. Thank you, sir, for chairing the session so well. And now I request all the participants to switch on their camera so that we can take another group photo for this keynote session. And then we will be starting the parallel sessions.
I think the photo has been already taken now.
Second plate, last time you missed. Another participant, some more participants are there. The second plate. They also should be.
Ma'am, we forgot to announce.
Time, last see how many are there in the second. Professor Kala is there. So many are there. That also should be taken.
Yes, ma'am. Ma'am, we'll make sure that from all the next sessions we'll take a picture.
Yeah. You have to take. You have to see how many plates are there.
Yeah.
Ma'am, we are taking screenshot of all the screens one by one.
But last time the first you took only one screen.
No, all the screens we have taken.
You have taken all the screens.
Technical person has taken all the screens.
Okay, then that's okay. Did not look because it not come.
Okay, then.
Okay. Yeah. So now I request all the participants to join any one of the parallel sessions using the links, the respective links provided in the email and WhatsApp earlier. And the sessions will start just immediately after this. And I also request all the paper presenters to be ready for their turn. And you may join the session just after this, okay? Thank you so much. Now we'll meet in the parallel sessions.